Time slows down when you move very fast. This is not science fiction, it is real. Albert Einstein showed us this in his theory of special relativity. When you travel close to the speed of light, time moves slower for you compared to someone who stays still. This strange idea is called time dilation. Imagine you are on a spaceship. You take off from Earth and travel at 90% of the speed of light. You fly straight for 5 years, turn around and come back. You feel like you were gone for 10 years. But when you return to Earth, you see that more than 20 years have passed for the people who stayed behind. You have aged 10 years, but your friends have aged 20. That is time dilation. The faster you go, the slower time passes for you. At everyday speeds, like driving a car or flying in a plane, the effect is tiny. You will never notice it. But as you get closer to the speed of light, the effect grows. At 99% of the speed of light, time for you moves about 7 times slower than on Earth. At 99.999%, the difference is huge. 1 year for you could mean hundreds of years for someone else. This does not break time. It follows the laws of physics. Clocks still tick. Your heart still beats. Your thoughts move along. Nothing feels strange to you. It is only when you compare your time with someone else's that you see the difference. One way to understand this is by looking at light. In Einstein's theory, the speed of light stays the same for all observers. It does not matter how fast you move. Light always travels at about 300,000 kilometers per second. That is fast enough to circle the Earth more than 7 times in 1 second. To keep light moving at the same speed, space and time have to adjust. Time slows down for fast-moving objects so that the math works out. If you are in motion, your time stretches. That means fewer seconds pass for you compared to someone who is still. Let's take another example. Think of 2 twins. One stays on Earth. The other boards a spaceship and travels near the speed of light. After a few years, the traveling twin comes back. The one who stayed on Earth is now older. The one who went on the trip has aged much less. They were born on the same day, but now their birthdays do not match in the same way. This is called the twin paradox. It is not a trick. It is what the math and the experiments show. We have seen this with tiny particles that move fast in labs. These particles live longer when they travel close to the speed of light. Their clocks slow down. We even see it in GPS satellites. These orbit Earth at high speeds and far from gravity's pull. Both speed and gravity affect time. Engineers have to correct for these time shifts to keep GPS signals accurate. Without these changes, your GPS would give you the wrong location. Einstein's idea might seem strange at first, but it fits the facts. It comes from one basic rule. The laws of physics must look the same for everyone, no matter how fast they move, as long as they move at a constant speed. From that rule, and from the fixed speed of light, time dilation follows. You can picture this with a simple light clock. Think of a box with a light beam that bounces between 2 mirrors. If you are still, the beam goes straight up and down. If you move fast, the beam takes a longer path, like a zigzag. But the speed of light cannot change. To make the longer path work, time must stretch out. That is, your clock ticks slower. You do not feel this slowness because your whole body and mind slow down the same way. Time dilation is not like watching a slow movie. It is more like living in a room with different time walls. Inside, everything feels normal. Outside, much more is happening. No one has built a ship that goes close to the speed of light. But if we ever do, we could use this effect to move into the future. We would not go back in time. That is much harder, maybe impossible. But we could leap forward. Years or centuries could pass outside the ship, while just a few years pass inside. This is not magic. It is not bending time in loops. It is a shift caused by high speed. The person inside the ship is not doing anything strange. They are just moving fast. The time dilation happens by itself, from the rules of space and time. We call this a kind of time travel, not the kind you see in movies, but real travel into the future. You cannot go back and fix the past, but you can jump ahead by going fast enough. Physics allows it. Nature makes it possible. Einstein's theory also tells us this is not just about clocks or machines. It is about all of life. If you lived on that fast-moving ship, you would age slower. Your cells would take more time to divide. Your voice would take longer to speak a sentence. Your brain would process slower compared to someone on Earth. But again, you would not notice. It would feel normal. Time would feel like time. We test this theory every day. Particle accelerators push particles close to light speed. We see time stretch for them. Astronauts feel a small version of this. They age a tiny bit less than people on Earth. Not enough to notice, but enough to measure. Einstein gave us a strange idea, but he also gave us a way to check it. Over and over, the checks come back right. Time does slow down for fast travelers, not because clocks break, but because time itself shifts. It stretches, it bends, and when you come back, you find a world that has moved on without you. Time does not move at the same rate everywhere. It moves slower in places with stronger gravity. This effect is real. Albert Einstein predicted it in his theory of general relativity. It is called gravitational time dilation. It means that if you stand near something with a lot of mass, like a planet, a star, or a black hole, time moves slower for you than it does for someone farther away. Imagine you are standing at the top of a mountain. Your friend stands at the bottom. You both hold identical clocks. You start them at the same time. After a while, your friend's clock shows a slightly earlier time than yours. Your clock, at the higher point with weaker gravity, has ticked faster. The difference is very small, but it is there. We can measure it. This happens because gravity affects space and time. Einstein showed that mass bends space and time around it. The stronger the gravity, the more space and time stretch. That stretching makes time run slower near the mass. Gravity pulls on time as well as on objects. Now picture a much stronger example. Think of a black hole. A black hole has so much mass in such a small space that it bends space-time almost beyond limit. If you get close to a black hole, time slows down a lot. You would not notice this because everything around you, your body, your thoughts, your watch, would also slow down. But someone watching you from far away would see the difference. Suppose you lower a clock toward the edge of a black hole, but keep it from falling in. You stay far away and watch the clock from a distance. As the clock gets closer to the black hole, it ticks slower and slower. Just before it reaches the edge, the clock seems to stop. It does not really stop. It only looks that way to you. Time at the edge of a black hole nearly freezes compared to your own. If you could survive near that edge, what physicists call the event horizon, you could wait just a few minutes and come back out to find that years or even centuries have passed for others. You would have aged only minutes, but the world you knew would have aged much more. This is gravitational time dilation. You do not need to be near a black hole to see this effect. It also happens on Earth. The gravity here is strong enough to slow time, but only by a small amount. Clocks on the surface of the Earth tick slightly slower than clocks in space. GPS satellites orbit Earth at high altitudes, where gravity is weaker. Their clocks tick faster than clocks on the ground. Engineers have to adjust for this. If they did not, GPS would be off by several kilometers. The rules are simple. The closer you are to mass, the slower your time goes. The farther you are, the faster it goes. This is not about how you feel. You cannot sense the difference. But the clocks can. So can light. Light from near a massive object shifts to longer wavelengths. We call this gravitational redshift. It is another sign that time is running slow near mass. Here is a scenario. Two astronauts float in space near a planet. One stays in orbit far from the surface. The other goes down to the surface, near the planet's center. The one on the surface experiences more gravity. Time moves slower for them. After a few years, the astronaut returns to the ship. The one who stayed in orbit has aged more. They both followed the rules of physics. They both lived full lives, but their clocks do not match. We do not need to guess about these things. We have tested them. In 1976, NASA flew a hydrogen maser clock on a rocket. The clock went high above Earth, where gravity is weaker. It ticked faster than a matching clock on the ground. The results fit the theory. More recently, scientists put atomic clocks on airplanes and moved them to high altitudes. Again, the clocks in weaker gravity ran faster. Even raising a clock by a few feet makes a difference. In one experiment, researchers saw a measurable shift in time between the floor and the top of a lab bench. Time dilation from gravity matters for space travel. If you spend time near a large planet or star, your time will not match that of someone in deep space. This could affect signals, navigation, and even communication delays. Space agencies plan for this. It also matters for science. Black holes offer one of the best places to study time dilation. When stars fall into black holes, they seem to slow down and stretch. This is not just due to light bending. It is also because time itself slows near the black hole. The idea can feel strange. We are used to thinking of time as fixed, but it is not. Time flows at different rates depending on where you are. Mass affects that flow. The stronger the gravity, the more time slows. You might wonder how you could ever experience this. On Earth, you already do. If you live at sea level, your time runs a bit slower than for someone who lives on a mountain. You cannot notice it, but it is there. With precise tools, we can measure it. This is not science fiction. It is not theory alone, it is fact. Time and gravity are linked. You cannot change one without affecting the other. Einstein saw this early in the 1900s. Since then, we have tested it many times. It always holds up. Gravitational time dilation shows us that time is not one thing. It bends, it stretches. It flows at different speeds in different places. We live with that every day. Our machines and tools must respect it. So must our understanding of the universe. What Einstein showed was that space and time are not separate. They are part of one fabric. Mass pulls on that fabric. The pull changes how time moves. It slows time down. The more mass you have, or the closer you get to it, the slower time goes. That is how a clock near a black hole can run slower than one far away. That is how you can return from a deep gravity well younger than the people you left behind. Not because time broke, because time bent, because time obeys the rules of gravity. A wormhole is a theoretical tunnel through space and time. It could link two far-off places or even two different times. Physicists call it an Einstein-Rosen bridge. Albert Einstein and Nathan Rosen first wrote about it in 1935. They found a solution in Einstein's equations of general relativity that suggested such a structure could exist. It came from the same math that describes black holes. Picture space as a flat sheet of paper. If you draw two dots on the paper, the shortest path between them is a straight line. But if you fold the paper and let the two dots touch, the path between them becomes much shorter. A wormhole is like that fold. Instead of traveling across the long surface of space, you pass through a shortcut. This idea is not proven. No one has seen a wormhole, but the math allows for the possibility under special conditions. Wormholes would not just be shortcuts through space. They might also connect 2 points in time. That is because space and time are part of one thing, space-time. If you bend space, you also bend time. If a wormhole connects 2 places in space, it may also let you move from one time to another. This makes wormholes interesting for the idea of time travel. The classic wormhole model uses 2 black holes. One black hole pulls things in, the other pushes them out. A tunnel links them. If you fall into one, you might come out the other. The tunnel itself is the wormhole. In theory, it could connect a star in one galaxy to a planet in another, even if they are billions of light years apart. The problem is that such a wormhole would collapse too fast for anything to pass through it. The walls would pinch shut under gravity. To keep it open, something must push back. Physicists think that exotic matter might do the job. Exotic matter is a type of material that has negative energy. It is not like anything we find in daily life, but certain quantum effects hint that it could exist. If enough exotic matter could be placed inside the wormhole, it might hold the tunnel open long enough for something to pass through. Keeping a wormhole stable is one of the biggest challenges in the theory. Even small amounts of normal matter might cause the tunnel to collapse. The throat, the narrowest part, needs to be strong enough to resist these forces. Exotic matter might supply the needed pressure. Without it, the wormhole snaps shut before it can be used. Think of a practical example. Say you have a wormhole that connects New York and Tokyo. Normally, a flight takes over 12 hours. But if you stepped through the wormhole, you might appear in Tokyo in seconds. To make it even stranger, one end of the wormhole might be near Earth, and the other near a planet in another galaxy. A tunnel does not care about distance in the usual way. It is a hole through space itself. Now imagine you move one end of the wormhole at near light speed and then bring it back. Due to time dilation, time at that end will have passed slower than at the other end. This would create a time difference between the two mouths. If someone enters one end, they might come out the other before they left. This setup could allow backward time travel. It depends on extreme conditions, but the math works out. Time in this case is part of the tunnel. Such a machine would not break any known laws of physics, but it would require technology far beyond what we have now. The energy needs are huge. The control must be precise. The risks are high. Still, it shows how general relativity opens the door to strange but possible ideas. There are also limits. Wormholes, if they exist, might be tiny. Quantum physics predicts that tiny wormholes could appear at very small scales, the Planck length. That is far smaller than an atom. These quantum wormholes would open and close so fast that nothing could pass through. They would pop in and out of existence like bubbles in foam. Some researchers think there could be a way to grow one of these tiny tunnels into a large, stable wormhole. No one has figured out how. Science fiction loves wormholes because they make great tools for fast travel and time jumps. But in physics, they are treated with care. They are not magic. They are possible under the right rules, but no evidence yet shows that nature uses them. Still, they remain part of serious study. One area where wormholes could matter is in solving problems about black holes and information. Some physicists think wormholes could help explain how information escapes from black holes. This is still debated. Wormholes could also connect two black holes or even act as links between particles. There is a theory that says entangled particles might be connected by tiny wormholes. This idea, known as ER equals EPR, tries to link quantum mechanics and general relativity. In this theory, the ER stands for Einstein-Rosen bridges. EPR refers to a 1935 paper by Einstein, Podolsky, and Rosen about entangled particles. ER equals EPR suggests that wormholes and entanglement are the same thing, seen in different ways. It is not yet proven, but it shows how wormholes might help unify physics. Let's take another scenario. Suppose explorers find or create a stable wormhole with two ends. One is near Earth, the other is near a distant star. They send a robot through. It emerges near the star and sends back data. The time it takes depends on how stable the tunnel is. But the shortcut is far faster than any rocket could move. If a wormhole holds, people could follow. What they find on the other side might change how we think about travel, time, and distance. But building or finding such a wormhole remains beyond current tools. The idea stays in the world of theory, backed by the rules of physics, but still out of reach. Even if wormholes never become real, they help us ask the right questions. What is space? What is time? Can we bend or cross them in new ways? Einstein's NAF gives one possible answer: a tunnel that links places and times in ways we have not yet seen. We do not know if nature uses these tunnels, but the door is open. The equations allow for the path. Whether we ever walk it is still unknown. A Tipler cylinder is a theoretical object. It could allow time travel if built under the right conditions. The idea comes from general relativity, the same theory Albert Einstein used to explain how gravity bends space and time. In 1974, physicist Frank J. Tipler studied what would happen if you had a massive cylinder spinning at high speed. He found that if the cylinder were long enough and dense enough, it could twist space-time around it. This twist could allow someone to travel back in time by flying around the cylinder in a certain way. The key part is rotation. The cylinder has to spin fast, very fast. The faster it spins, the more it drags space-time around with it. This is called frame dragging. We already know frame dragging is real. Satellites around Earth have measured it on a small scale, but the Tipler cylinder needs much more mass and speed to create strong effects. It needs so much mass that it would crush anything nearby unless it was built with exotic materials or in space. In this model, if you flew a spaceship around the cylinder in a tight spiral path, you could return to a point in time before you started the trip. This works because the twisted space-time curves so much that the usual order of cause and effect breaks down. Events can loop back on themselves. Physicists call this a closed time-like curve. Time is still flowing forward inside your spaceship, but the path it follows loops back to an earlier point in outside time. To understand this, imagine a ribbon. If you stretch it straight, it represents normal time. But if you twist it into a spiral, then loop it, you can touch one part of the ribbon to an earlier part. The ribbon is still one smooth line, but its shape allows you to go from one point in time to another. That is what space-time would do near a Tipler cylinder. The catch is that the cylinder must be infinitely long. A finite-length cylinder does not create the right twist. It either does not form a closed loop in time, or it creates one that breaks down under its own gravity. This makes the Tipler cylinder more of a thought experiment than a blueprint. No one can build something infinite. Still, the math shows what general relativity allows under perfect conditions. Some later models suggest that you could get similar effects with a very long, but not infinite, cylinder if you use exotic matter. This is material that has negative energy density. Normal matter has positive energy. Exotic matter bends space-time in the opposite direction. If you line the cylinder with exotic matter, you might stop it from collapsing and get the time travel effect with a shorter object. Exotic matter is rare, and we have not found large amounts of it, but quantum physics suggests it could exist. Another challenge is speed. The cylinder must rotate near the speed of light. This creates huge forces. The material of the cylinder would need to withstand enormous pressure. Any mistake or weakness would tear the cylinder apart. The energy needed to keep it spinning would also be vast, far beyond what current technology can handle. Even if you built such a cylinder and flew around it the right way, time travel might still fail. Small changes or disruptions in space-time could destroy the closed, time-like curves. Some physicists think that once you add quantum effects, the curves vanish. Others think nature might have rules that prevent time loops to avoid paradoxes. Paradoxes are a problem with time travel. If you go back in time and change something important, like stopping your own birth, it creates a contradiction. The Tipler cylinder allows time loops, but it does not explain how these contradictions are avoided. Some theories suggest that the universe would not let you change the past. Others say there could be many timelines, and your trip would move you to a different one. These ideas go beyond the original cylinder model, but they show why time travel is not just about building machines. It also depends on how the universe handles cause and effect. Let's say you did have access to a stable Tipler cylinder. You approach it in a spaceship. You follow the right path, a spiral that hugs close to the cylinder's surface without hitting it. As you move forward in time inside your ship, your path bends back to a past moment in outside time. When you exit the loop, you arrive before you started. For you, time has flowed as normal. But your location in the universe's timeline has changed. You are now earlier than when you began. This would not be like jumping in and out of time. You would have to move carefully. If your path does not match the exact shape of the closed Timelike curve, the effect will not work. You might fly by the cylinder and notice nothing. Only the precise loop causes backward time travel. Navigating such a path would take exact calculations and control. The forces near the cylinder would be intense. The curved space-time would push and pull on your ship. You would need to protect your body from these shifts. The closer you fly, the stronger the effect, but also the greater the risk. Any mistake could push you into the cylinder or fling you away. And if the cylinder is unstable, the entire path could collapse during your trip. No one has ever built or seen a Tipler cylinder. It remains a part of theoretical physics, but it shows how general relativity allows for the bending of time under extreme conditions. The same math that describes how gravity curves space also predicts these strange loops in time. The idea helps physicists explore the limits of time, motion, and causality. It raises questions about what the universe allows and what it prevents. Even if the cylinder stays a theory, it shapes how we think about time travel. It pushes us to consider not just if time travel is possible, but what rules and structures time itself follows. A closed time-like curve is a path through space and time that loops back on itself. It allows an object to return to the same point in space and time where it started. This kind of path is a solution to Einstein's equations of general relativity. The idea may sound like fiction, but the math checks out. Under certain conditions, space and time can bend so much that cause and effect form a circle. Timelike means the path is one that a real object with mass can take, something slower than light. Closed means the path ends where it begins. If you followed a closed time-like curve, you would live forward in time along the path, but end up in your own past. You would not feel anything strange. Your watch would tick forward, your body would age, and your thoughts would flow normally. But when you complete the loop, you would arrive at a point in time that already happened. These curves appear in several known solutions to Einstein's field equations. The Tipler cylinder is one. A spinning object, under the right conditions, can drag space and time around it. If it spins fast enough, it can twist space-time into a loop. Another example is the Kerr black hole. This is a rotating black hole. The math says that inside a Kerr black hole, time might also form loops. These areas are deep inside the event horizon, where no signal can escape, but the equations say closed time-like curves are possible there. There's also the Gödel universe. In 1949, mathematician Kurt Gödel found a solution where the whole universe rotates. In this model, time loops appear naturally. You could travel in a spaceship and return to your own past. Gödel's model does not match our universe. It has no expansion and no cosmic background radiation, but it shows what relativity allows. Physicists use these cases to ask what is possible in principle. If general relativity is correct, and if space-time can be curved enough, then time loops might exist. But building or reaching them is another story. Imagine a scenario. You are an astronaut. You fly along a closed time-like curve near a rotating object. You leave your ship at noon. You follow a precise path. Your clock shows time moving forward, but when you return, it is still noon. You walk into the room you left. From the outside, you are in two places at once, leaving and arriving at the same time. To you, there is no conflict. Your timeline makes sense. The world's timeline does not. This raises the question of paradoxes. What if you meet your past self and change something? What if you stop your own departure? That would break causality, the rule that cause comes before effect. Some physicists argue that the universe avoids these problems. One idea is the self-consistency principle. It says that any action you take while inside the time loop must already be part of history. You cannot change the past, because your actions are already woven into it. Let's take an example. You go back in time to give your younger self a message. Your younger self grows up, remembers the message, and gives it to the past version. The loop holds. The information has no starting point. It exists only because the loop keeps it alive. This seems strange, but the logic holds. The cause and effect support each other in a circle. This is called a causal loop. Objects, events, or information exist in the loop without an outside origin. They are self-contained. It does not break physics, but it challenges our normal ideas of time. We expect causes to come before results. In a closed time-like curve, the two feed each other. Quantum mechanics adds more questions. It may not play well with closed time-like curves. Some calculations suggest that time loops could allow strange events, like copying a particle perfectly or sending information faster than light. These things are not allowed in regular physics. To avoid these problems, some theories suggest that the laws of nature stop time loops from forming in the first place. This is called the chronology protection conjecture. Stephen Hawking proposed it. He said that even if time loops are allowed by general relativity, quantum effects might stop them. The universe would protect its timeline. We do not know if this is true. The question is still open. Closed time-like curves remain possible in the math. Whether nature uses them is unknown. If they do exist, they might be hidden inside extreme environments, places like black holes or the early universe where we cannot test them directly. Engineers and physicists have also studied artificial ways to create closed time-like curves. One idea is to use wormholes. If you move one end of a wormhole at high speed and then bring it back, the time at that end will fall behind. This creates a time shift between the two ends. If you enter the younger end, you could exit at the older one, arriving before you left. The path between the two ends forms a closed time-like curve. But this idea needs stable wormholes and exotic matter, both of which are still beyond our reach. Another proposal uses massive rings of light. A physicist named Ronald Mallet suggested that a strong beam of circular laser light could twist space-time and form a loop. The effect would be small, but it could in theory create a closed time-like curve. Like the other models, it needs very specific conditions. Even if a closed time-like curve could be built, using it would be risky. A small change could break the loop. The energy needed might be huge. The forces involved could tear a ship or a person apart. Even a single atom falling into the loop could change the outcome. These problems make time travel by closed time-like curves more of a thought tool than a real project. Still, closed time-like curves help physicists explore the structure of time. They force us to ask hard questions. Is the past fixed? Can information exist without origin? What does it mean to travel through time while aging forward? The answers are not clear, but the curves are part of the rules as far as we can tell. They show that time might be more flexible than it seems. Relativity does not say time must always move forward in a straight line. Under the right conditions, it can bend, twist, and even form a loop. Whether nature allows those conditions is still unknown, but the math opens the door. The closed time-like curve is what lies behind it. Cosmic strings are theoretical objects that may have formed just after the Big Bang. They are not strings like you find in fabric. They are long, thin tubes of energy stretched across space. Scientists believe they could be as narrow as an atom, but have so much mass that a single kilometer of one would outweigh a planet. These strings may be leftovers from when the early universe cooled and expanded. Just like cracks can form in ice when water freezes. These defects in space may have appeared as the universe settled into its present state. No one has seen a cosmic string, but their possible effects come from the math of general relativity. That math tells us how mass and energy shape space and time. Because a cosmic string is so dense, it would warp space-time around it. It would not bend space in a way that pulls you toward it, like a planet or a star. Instead, It would create a sharp angle in space. If you walked in a circle around a cosmic string, you would find that you hadn't turned a full 360 degrees. You would be back where you started, but the angle would be smaller. This kind of space is called conical geometry. That alone would not make time travel possible, but in 1991, physicist J. Richard Gott suggested that under the right conditions, two cosmic strings could allow for closed time-like curves. These curves are paths through space and time that loop back on themselves. If you traveled along one, you could return to your own past. The idea works like this. If two cosmic strings moved past each other at near the speed of light and in just the right way, the space around them could bend enough to form a time loop. You could start at one point in space, fly around the two strings, and end up at an earlier time. Your own clock would keep ticking forward, but the path through space-time would carry you into your past. This would not be magic. It would be a natural result of how gravity and motion twist time. To understand this, imagine a flat sheet of rubber stretched tight. Now press two very heavy pencils into it and drag them past each other quickly. The rubber bends and stretches in sharp ways. Cosmic strings would do something similar to the fabric of space. Their speed and mass would make the bending strong enough to affect time. There are rules. The strings would have to move very fast, close to the speed of light. They would also have to avoid touching or colliding. If they met, they could snap or release energy. The conditions must be just right to form a stable loop in time. Even small changes in speed or angle could break the effect. If such a loop did form, you could use it to travel back in time. Imagine a spacecraft flying around the two strings in a specific path. The pilot starts the journey at noon. The ship circles the strings. When it emerges from the path, the clock outside reads 11:45 a.m. The ship has arrived 15 minutes before it left. Inside, everything felt normal. Time moved forward, but the ship's position in the larger timeline has shifted. The effect depends on the exact shape of space-time around the strings. The path must be a closed time-like curve, one where time and space both bend in a way that allows a return to the same moment. These curves are not common. They need extreme conditions to exist, but the math shows that cosmic strings could, in theory, make them. We have not found any cosmic strings. They remain a guess based on what we think happened during the early universe. If they exist, they may stretch across galaxies or form loops that oscillate and decay. Some theories say they might radiate energy as gravitational waves, ripples in space that we can now detect with tools like LIGO. If a cosmic string passed through our part of the universe, it might leave signs we could spot, like sharp shifts in light or background radiation. Some scientists have looked for signs of lensing, where a cosmic string bends the light of distant stars, but nothing has confirmed their existence so far. Even if they do exist, they may not be the kind we need for time loops. Their speed, shape, and mass would all matter. If they do not move fast enough or come in the wrong arrangement, they won't cause the right warping. The idea of using cosmic strings for time travel also faces technical limits. The energy needed to bring two strings close and move them at near light speed would be immense. Controlling them without causing collapse or uncontrolled release of energy would be a huge challenge. There's also the issue of stability. Even if a time loop formed, small changes might tear it apart. Quantum effects, like tiny fluctuations in energy, could build up and stop the loop before anything travels through it. There's also the question of paradoxes. What happens if you go back in time and stop your own trip, or change something that prevents the loop from forming? The laws of physics allow the loop, but do not tell us how the universe would handle these contradictions. Some theories say events in a time loop must stay consistent. You can't change the past, you can only take part in it. Others say different timelines might split off when you interfere, making a new version of history. These ideas go beyond the original string model, but are important if time travel ever becomes real. Still, cosmic strings offer a clean and testable idea. They come from real math and known physics. They do not break the laws of nature, but instead use them in an extreme way. If we ever find one and learn how to work with it, the door to time travel might be open, not with machines or portals, but with the natural shape of the universe. In theory, a pair of cosmic strings moving at the right speed could bend space and time into a loop. That loop could carry you backward in time. Even while your own clock moves forward, you would not feel anything strange. The journey would seem smooth. But when you returned, the universe around you would be younger than when you left. Time in that case would not just pass, it would twist, and the string, silent and dense, would be the tool that made it happen. Quantum tunneling is a strange effect that comes from the laws of quantum mechanics. It lets particles cross barriers they should not be able to pass. This behavior does not follow the rules of classical physics, where something must have enough energy to climb over a wall or push through an obstacle. In the quantum world, a particle can appear on the other side of a barrier without ever going over it. The math says that the particle's wave function, the shape that describes where it might be, is not limited by the barrier. Instead, it stretches through the barrier and beyond it. There is a small chance that the particle will be found on the other side, as if it had skipped the wall entirely. Scientists see quantum tunneling in labs all the time. It happens in semiconductors, where electrons tunnel through insulating layers. It plays a role in nuclear fusion, where protons in the sun tunnel through the energy barrier that would normally keep them apart. These are not rare effects, they are real and measurable. But when we start to ask whether tunneling can allow travel through time, the answer is less clear. Some researchers have explored whether tunneling could let particles move not just across space, but across time. The idea is that just as a particle can jump from one location to another without crossing the space between, it might jump from one time to another without passing through the moments in between. This is still very theoretical. No one has seen it happen, but the equations that describe tunneling have features that make people wonder. One strange part is the timing. In some cases, the time it takes a particle to tunnel through a barrier seems shorter than expected. In fact, it can seem like the particle arrives on the far side of the barrier faster than it would have if it had traveled at the speed of light through normal space. This has led to claims that tunneling might involve some kind of faster-than-light effect, or even backward movement through time. However, most physicists think this is not the right way to see it. The particle does not really break the speed of light. The apparent speed is a side effect of how the wave function spreads out and how we measure it. Still, the idea of quantum time travel through tunneling has not gone away. Some models suggest that under the right conditions, a quantum system might form a loop in time. This would be a version of a closed Timelike curve, but based on quantum rules instead of gravity. For example, a particle might enter a barrier, disappear, and reappear at an earlier moment on the other side. It would have tunneled not just through space, but into the past. One way to explore this is with quantum circuits, systems made of particles or qubits that follow quantum rules. In 2019, a group of scientists simulated a tiny version of time reversal on a quantum computer. They used a process to make a qubit return to a previous state. It was not real time travel, and it only worked for a few steps. But it showed how quantum systems might be pushed to behave in time-bending ways under tight control. Another concept comes from quantum entanglement. When two particles are entangled, their states are linked, no matter how far apart they are. A change in one shows up in the other instantly. This does not allow messages to travel faster than light, but it raises deep questions about how time and causality work in quantum systems. Some researchers have proposed using entanglement and tunneling together to create shortcuts through time. The math is complex, and the results are not settled, but it shows how quantum theory blurs the line between space and time. One challenge is that quantum systems are delicate. Any interaction with the outside world can cause them to lose their quantum behavior. This is called decoherence. For quantum tunneling to be used in time travel, the system must stay isolated and controlled. That is hard to do, even in simple experiments. And even if we could control it, we would still face the problem of scale. Quantum effects happen at the level of atoms and particles. We do not know how to extend them to larger systems, like people or machines. Let's take a thought experiment. Suppose you have a particle in a box with a barrier in the middle. The particle starts on the left side. You measure it and find that it is there. Then you wait, and after some time, you measure again. Now it is on the right side. The particle did not have enough energy to climb over the barrier, but it tunneled through. Now imagine that the particle's presence on the right side also triggers an event that happens earlier than when it left the left side. If this were possible, then the particle would have tunneled into the past. The timing would form a loop. But we don't know if this can happen in real life. So far, the experiments do not show clear evidence of time loops from tunneling. Even if quantum tunneling does not let us travel through time, it still changes how we think about time. In classical physics, time moves forward in a straight line, and particles follow predictable paths. In quantum mechanics, paths are uncertain, and time can be part of a range of outcomes. When a particle tunnels, it does not take a known route or move at a known speed. Its journey is a cloud of probabilities. Time, in this view, is not a line, but a spread of chances. Some physicists argue that quantum mechanics might allow time travel as long as the timeline stays consistent. In this view, a particle that travels into the past must do so in a way that avoids paradoxes. It cannot change anything that would prevent its own journey. This is called the self-consistency principle. It matches the idea that all events in a quantum loop must fit together without contradiction. If quantum tunneling ever allows time travel, this rule might help explain how it works. Others believe that quantum tunneling could link different timelines. Instead of going back into your own past, a particle might enter a different branch of reality. This would avoid paradoxes, but raise questions about how timelines split and whether we could ever observe or return from another one. These ideas are part of the many worlds interpretation of quantum mechanics, which says that all possible outcomes happen, each in its own universe. Quantum tunneling shows us that particles do not follow fixed rules the way large objects do. They can cross boundaries that seem impossible. Whether this includes crossing time remains an open question. The theory leaves room for strange things. What we lack is proof that they happen. For now, tunneling remains one of the most unusual effects in physics, one that opens the door to deep questions about what time really is. Tachyons are theoretical particles that always move faster than light. No one has ever seen one, and no experiment has found proof they exist. Still, the idea fits within the math of special relativity. In fact, if we follow the logic of Einstein's equations, it turns out that particles faster than light are not strictly forbidden. They are just very strange. One of the strangest parts is this: tachyons, if they exist, would not follow the usual rules of cause and effect. In some situations, they could send signals backward in time. In normal physics, nothing with mass can reach the speed of light. As an object moves faster, it gains more energy. To push it closer to light speed, you must give it more and more energy. At the speed of light, the energy needed becomes infinite. That's why objects like rockets, atoms, or people can never break this barrier. But Einstein's theory doesn't stop us from imagining something that always travels faster than light. In this case, we are not trying to speed it up from a slow start. We're starting with something that already moves faster than light and stays that way. That's what a tachyon would be. Its speed is never below the speed of light. In fact, if it tried to slow down, it would need more and more energy to do so. It could never slow down to light speed, just as we can never speed up to light speed. Tachyons would have imaginary mass. This does not mean they are made up or fake. It's a math term. In equations, their mass includes the square root of a negative number. That's what gives them the ability to go faster than light. Because of that, their energy and momentum behave in ways that flip some parts of normal logic. One effect is reversed causality. In most cases, a cause happens first, and the effect follows. You flip a switch, and then the light turns on. But with tachyons, different observers moving at different speeds could disagree about the order of events. One person might see the tachyon get sent. Another person, moving fast in another direction, might see it arrive before it was sent. This means the effect happens before the cause. To see how this works, imagine you're standing still and your friend is running past you. You send a tachyon to them. Because it moves faster than light, it beats the light signal. But from your friend's point of view, time is flowing differently. In their frame, the tachyon might appear to arrive before you sent it. It looks like the effect came before the cause. This kind of reversal could lead to paradoxes. For example, what if you used a tachyon to send yourself a message that stops you from sending the message in the first place? These problems are part of why many scientists think tachyons are not real. They may be artifacts of the math, possible on paper, but not in the world. Still, the math of special relativity doesn't forbid them outright. It just shows that if they exist, the rules we're used to no longer apply. Causality, one of the basic ideas in physics, would need to be rewritten. There have been some efforts to use tachyons in field theories. In quantum field theory, a tachyon shows up as a particle with negative mass squared. This usually means the theory is unstable. Instead of predicting real particles, the presence of a tachyon signals that something is wrong with the setup. You need to change the field or the model to fix it. In string theory, tachyons appeared in early versions as signs of instability. Once the theory was improved, the tachyons disappeared or were reinterpreted. Despite these problems, the idea of tachyons has helped physicists test the limits of their theories. If something like a tachyon did exist, what would it mean for the structure of space and time? Could information move backward? Could we send signals into our own past? Let's take an example. Say you build a device that can detect tachyons. You arrange it so that it receives a tachyon pulse from the future. When it detects the pulse, it triggers an alarm. The alarm warns you not to send the pulse after all. But if you cancel the pulse, then the alarm never goes off. And if the alarm doesn't go off, you send the pulse again. This is a causal loop. The outcome keeps feeding into the beginning. It makes no clear sense. This is why many physicists believe that if tachyons could exist, something would have to prevent them from creating loops like this. One idea is that even if tachyons exist, they cannot be used to send information. The signal might be scrambled, or the process of creating it might destroy the pattern. You could detect the presence of a tachyon, but not use it to carry a message. That way, causality is safe, even if faster-than-light particles exist. Another idea is that all observers would agree on what happens if they follow strict rules of how time and motion work in relativity. Even if some observers see the order of events flip, the math might work out in a way that prevents paradoxes from forming. This is still debated. Some researchers have looked at how tachyons could relate to time travel. If you could move faster than light, could you use that to loop through time? In many cases, faster than light travel does open the door to time travel, at least in theory. But again, the same problems show up: reversed causality, paradoxes, and logical breakdowns. There's also the question of energy. Creating or interacting with a tachyon might require infinite or undefined energy. This would make it impossible to use in any real experiment. It might also mean that tachyons can't interact with normal matter in a useful way. They would pass through space without touching anything, like ghosts. Some people have looked for signs of tachyons in cosmic rays or in experiments with high-energy particles, but no signal has matched the expected properties. If tachyons exist, they are either very hard to detect or simply not present in the parts of the universe we can observe. In particle physics, the term tachyon sometimes refers to something else, a sign that a field is unstable and needs to shift to a more stable state. This is different from a real particle flying faster than light. It's more like a clue in the math that the system wants to settle into a different energy level. In these cases, the tachyon is not something you can see or use. Still, the idea of tachyons helps explore how much we really know about time and motion. Even if they don't exist, asking what they would mean forces us to think about causality, speed, and the limits of physics. The concept shows that even settled theories like relativity can contain surprises, paths the math allows, but nature may not take. Whether the universe has hidden layers that allow faster-than-light effects is still an open question. But for now, tachyons remain part of the story physics tells when it pushes against the edges of the known. The block universe is a way of thinking about time and reality. It says that all moments, past, present, and future, exist at once. Nothing is truly moving. Instead, everything that has ever happened or will happen is part of a fixed structure. Time does not pass. We just experience different parts of this structure at different points in our lives. This idea comes from the theory of relativity, which changed how we understand space and time. In everyday life, time feels like it flows. You wake up, eat, work, rest, and sleep. Things change. Events unfold. The future becomes the present, and the present becomes the past. This flow feels real. But the block universe says that this feeling is an illusion. Time is not something that flows. It is more like space, something that exists in full, whether we see all of it or not. Imagine a long road that stretches for miles. You stand on one part of the road, and you see only the section near you. But the entire road still exists, even the parts you cannot see. The block universe says time works the same way. Right now, you are in one moment, just as you are in one place. But all other moments, your childhood, tomorrow morning, events 1,000 years from now, also exist. You just are not standing at them now. This view is based on the way Einstein's theory of relativity connects space and time. In special relativity, there is no universal now. Two people moving at different speeds may not agree on when an event happens. One person might say a lightning bolt struck at noon, while another says it struck at 12:01. Both are correct in their own frames. This means there is no single shared present. If there is no shared now, then the idea of a moving present makes less sense. Instead of thinking of time as something that passes, we can think of space-time as a four-dimensional shape. 3 dimensions are space, and 1 is time. Your life forms a line through this shape. That line, called a world line, includes every point in time where you exist. From your birth to your death, your entire life is laid out in space-time. You do not move along that line. You are already there at every point. Your awareness or consciousness moves or seems to move, but the line itself is fixed. This way of thinking is called eternalism. It says all events exist equally. Your birth is just as real as this moment right now. So is your death. The fact that you feel present in this one moment is not because only this moment is real, but because your brain processes information in a certain way. It remembers the past and predicts the future. It creates a sense of time flowing, but that flow is part of your mind, not part of the world. You can compare this to watching a movie. The entire movie exists on the film reel, or in the digital file. But when you watch it, you see only one frame at a time. You feel tension, joy, or sadness as the story unfolds. Still, every scene, the beginning, middle, and end, is already there. The movie does not change. Your experience of it changes as you move through it. The block universe treats time in a similar way. All scenes of your life already exist, even the ones you haven't seen yet. Let's take an example. Suppose someone is walking down a sidewalk. They raise their hand to wave. In the present moment, you see the arm lift. But in the block universe, every part of that wave, starting, rising, peaking, and falling, is already part of the structure. Nothing needs to move. The wave is a static pattern laid out in time, just as a statue is laid out in space. Now imagine two people watching this wave. One is standing still. The other is on a fast-moving train. Due to special relativity, they may not agree on the order of events. One might say the person waved first and then smiled. The other might say the smile came before the wave. Both are right in their own frame of reference. This means time is not absolute. If the order of events can change depending on who observes them, then maybe events themselves are not tied to one fixed timeline. They are all just parts of the block. This view also changes how we think about free will and choice. If the future already exists, are our decisions fixed? Do we choose, or are we just following the path that's already there? In the block universe, your choices are part of the shape of space-time. The decision you make tomorrow is already in place, just like the choice you made yesterday. That does not mean you are not making the choice. It just means the act of choosing is part of a wider pattern that exists beyond your current point of view. Some people find this idea unsettling. It suggests that you cannot change what happens, because everything already exists. Others find it calming. It means that nothing is ever truly lost. The past is not gone. It still exists in its place in the block. Your happiest memories, the people you miss, the moments you wish could last forever, they still exist in their slices of time. You are just no longer standing in those parts. This view also affects how we see death. In the block universe, death is not the end of your existence. It is simply one point on your world line. You still exist at earlier times. Those times do not vanish. They are fixed in the structure. Someone reading the book of space-time could flip back to those chapters and see you there. To them, you are still alive in those moments. Even physics treats time this way in some situations. In quantum mechanics and thermodynamics, equations often look the same forward and backward. They do not require a flow of time. The laws of nature do not seem to prefer one direction. Time's arrow, our sense that the past leads to the future, comes from things like entropy, memory, and heat. It does not come from the basic rules of the universe. Some scientists argue against the block universe. They prefer models where time is active, changing, or growing. But so far, the math of relativity supports the block view. It treats all moments as equally real. If we accept that, then the passage of time is not part of nature. It is part of how our minds work. The block universe tells us that the entire cosmos is already there. Every star's birth, every life, every word you speak, all exist in a complete structure. You are not traveling through time. You are part of time, spread out across it like a mountain across space. Your presence in this moment is one small piece of the whole. The rest is still there, waiting in its place. Some theories in physics treat time as a dimension like space. Instead of thinking of time as something separate or flowing, these ideas describe it as another coordinate in a larger framework called spacetime. In this view, time is not a river that moves us forward. It is more like a direction, a line you can plot, measure, and possibly move through, just as you move through space. This approach comes from Einstein's theory of relativity. In special relativity, space and time are not separate things. They are connected and form a single four-dimensional structure. 3 dimensions of space and 1 of time. Events do not just happen at places like here or there. They happen at points in space-time, defined by location and time together. This union of space and time means we need to think differently about what time is. In everyday life, space and time feel different. You can move freely in space. You can walk forward, backward, left, and right. Time seems different because you move through it in only one direction, forward. You can't pause, reverse, or skip ahead. That gives time a special status in your mind. But in space-time, this difference may not be as deep as it feels. Time might just be one more coordinate, just harder to move through in more than one direction. To understand this, imagine a map. You can point to a spot and say it's 3 miles east and 2 miles north. That gives a location in space. Now add time. Say something happened at that location at 5 p.m. You now have a full description of an event. 2 space dimensions and 1 time dimension. For real events, we need 3 dimensions of space and 1 of time. That gives us 4 numbers, coordinates in space-time. Einstein showed that the laws of physics look the same for people moving at constant speeds, even if they're moving differently. To make that work, he had to change how time behaves. If 2 people move at different speeds, they will measure time differently. One might say a second passed, while the other says it was longer or shorter. This is time dilation. It shows that time is not absolute. It depends on your motion, just like space does. Because time behaves this way, it fits into the same framework as space. They are not the same in every way, but they are linked. Together, they form a kind of landscape. Just like you can trace a route through space, you can trace a path through time. Physicists call this path a world line. It shows where and when something exists. You are not just at a place, you are at a time and place. Some theories go further. They suggest that time might be more like space than we think. If time is a dimension, can we travel through it like we do through space? Can we go forward and backward, not just one way? In normal life, you always move forward in time. This is tied to how your brain works and how the universe seems to behave. But in the math of relativity, time can go in either direction. The equations do not prefer one direction over the other. The path you take through space-time could, in theory, bend, loop, or curve, just like a path through space. For example, in some solutions to Einstein's equations, time can form loops. These are called closed time-like curves. If you followed one, you could return to an earlier point in time. This is not science fiction. It is a real part of the math. But building or using such a loop would require extreme conditions, like massive spinning objects or exotic matter. We do not know if those things exist in a useful form. Even if time is a dimension, that does not mean we can move through it freely. You can stand still in space or change your direction, but you cannot stand still in time, and you cannot choose to turn around. Something keeps pushing you forward. That something might be entropy. Entropy is a measure of disorder. It tends to increase over time. A glass falls and breaks, but it does not unbreak. A candle burns, but it does not reform. This rise in entropy gives time its arrow. It points from order to disorder. That arrow may explain why you feel time moving in one direction. It is not built into the equations, but it comes from the way the universe started, with low entropy. But the idea of time as a dimension suggests that past and future are just as real as the present. They exist along the timeline, just as other places exist along a road. You experience the present moment, but all moments are there. You do not move through time in the sense of something flowing. Instead, your consciousness might jump from one part of the timeline to another, like reading a page in a book. Let's take an example. You are sitting in a chair, reading this sentence. You remember having breakfast. That memory gives you the sense that the breakfast is in the past. You might think about what you'll do tomorrow. That plan gives you a sense of the future. But in space-time, all these events, breakfast, reading, tomorrow's work, already exist. They are spread out across the time dimension. Some physicists describe time as a static landscape. All events are there, fixed in place. You do not move along time. You exist at a point in the landscape, just like you exist at a place in space. Your sense of moving through time may come from how your brain processes memories and expectations. There are also models in physics where time and space can trade places. In some parts of black hole theory and early universe models, time behaves like a space dimension. Near the Big Bang or inside certain horizons, time can flip roles with space. This shows that time may not be as rigid or unique as it seems. In quantum gravity and other advanced theories, time becomes even less clear. Some models do not have a time variable at all. They treat events as relations between objects, not as things that happen in sequence. In these cases, time is not a fundamental part of reality. It is something that comes out of more basic rules. Still, for now, you live in a world where time feels like a flow. But the physics says otherwise. Time might just be another dimension. You may not travel through it the same way you walk down a street, but it exists, in full, with all its moments lined up. You are in one of those moments now. The rest are still there, before you, after you. Not gone, not waiting, just part of the larger structure that makes up reality. The Grandfather Paradox is a thought experiment about time travel. It asks what happens if you go back in time and change something that would prevent your own existence. The usual version is simple. You travel back and kill your grandfather before your parent is born. If you succeed, then your parent is never born and neither are you. But if you are never born, you cannot go back to kill your grandfather. That means he survives, your parent is born, and so are you, so you can go back. This loop has no clear answer. It circles without a logical end. That's what makes it a paradox. This kind of problem shows up in many time travel ideas. The paradox happens when you change the past in a way that removes the reason you went back in the first place. If you undo your own existence, you also undo the event that let you change things. That breaks cause and effect. The cause no longer leads to the effect. It cancels itself out. The loop becomes unstable. The grandfather paradox is not really about family. It could involve anything where past and future depend on each other. You could go back and stop the invention of a time machine. If you do that, then the machine was never made and you could not use it to go back. The same problem appears. Or you could go back to stop a war, and if you succeed, the war never happens. Without the war, you have no reason to go back. These loops create contradictions that normal logic cannot fix. In physics, this is a serious problem for time travel into the past. Many of the laws that describe how things move and change assume that cause comes before effect. This is called causality. You strike a match, then it burns. You open a door, then you walk through. Time flows forward. The grandfather paradox flips that. It lets effects happen before their causes, and then lets those causes disappear. Some theories try to solve this problem by saying the past cannot be changed. If you go back in time, anything you do must already be part of history. This idea is called the self-consistency principle. It says you can visit the past, but you cannot change it in a way that creates a contradiction. If your grandfather died young, then something stops you from killing him. Your gun jams. You get sick. Or maybe you don't even try. Something always blocks the paradox. History protects itself. In that view, the trip to the past still happens. You were always part of that past. Whatever you did there already happened. You might inspire your grandfather to do something new. You might even save his life. But you cannot erase yourself. That would violate the logic of a consistent timeline. Other theories offer a different answer. They suggest that when you change the past, you don't rewrite your own timeline, you create a new one. In this view, time is not a single thread, it branches. When you go back and kill your grandfather, you create a new branch where he dies. In that world, your parent is never born, and neither are you. But the version of you who went back came from a different branch, one where your grandfather lived. This idea comes from the many worlds interpretation of quantum mechanics. In that model, there is no paradox. Each change starts a new version of history. The timeline splits, and each version runs on its own. The universe where you came from still exists, and so does the new one you changed. You are not erasing yourself. You are creating a copy of the world with different rules. But this raises other questions. Can you ever return to your original timeline? Do you still have a home if every trip makes a new branch? Some versions of this theory suggest that you can never go back to your own past. You can only move into a copy that looks like the past. That copy has the same people and events, but it is not the one that made you. In that case, the grandfather paradox does not apply. You can change things in the copy, but the original version that led to you still exists elsewhere. There's also the idea that time travel to the past is just not possible, no matter what theory you use. Some physicists argue that the universe has built-in rules that prevent paradoxes. This is the idea behind the chronology protection conjecture proposed by Stephen Hawking. It says that even if time loops are allowed in theory, nature will stop them from forming in practice. Quantum effects might destroy them. Random changes in energy could build up and block them. Time machines would break before they work. If this idea is right, then the grandfather paradox never happens because the trip to the past is never allowed. Another view is that the paradox shows a gap in our understanding of time. Maybe time is not what we think it is. Maybe our ideas about cause and effect are too simple. Some researchers believe that quantum physics might offer ways to avoid the paradox, not by making multiple timelines, but by using probability. In that case, the past can shift in small ways, but never enough to break the link to the future. You could go back and try to kill your grandfather, but the odds of success might be zero. You could aim and fire, but the bullet would always miss. Some scientists have tested parts of these ideas using simulations. One study used a quantum computer to model how a particle might act if it entered a time loop. The system was set up to allow paradoxes, but the math found ways around them. The particle always behaved in ways that avoided a direct contradiction. It suggests that even in strange conditions, the rules might force events to stay consistent. In fiction, the grandfather paradox appears often. Stories use it to explore what it means to change the past. Some tales show the hero trapped in a loop. Others end with the world erased or rewritten. The paradox adds tension because it touches something deep, the need for things to make sense. We want the past to lead to the present. We want actions to have results. When time loops threaten that, they unsettle us. The grandfather paradox is more than a puzzle. It tests the limits of what we think time is. If time can be bent, traveled, or changed, what does that mean for memory, identity, and truth? If you can erase your own past, who are you in the present? If your future causes your past, then where does it all begin? These are not just questions for science. They are questions for anyone who wonders how time works and whether it can ever be undone. The Bootstrap Paradox is a problem that shows up in time travel. It happens when an object, idea, or piece of information exists in a loop with no clear starting point. Something appears to create itself. It seems to come from nowhere. This kind of paradox raises deep questions about cause and effect and about how time really works. One simple example involves a person who travels back in time with a book. Suppose she gives the book to someone in the past, who then copies it and publishes it. Over time, the book becomes famous. Centuries later, the time traveler reads it and brings it back again. The loop closes. But here's the problem. Who wrote the book? The traveler got it from the past, but the person in the past got it from her. There's no original author. The book exists, but its creation has no clear cause. This is what makes it a paradox. In normal life, things have origins. A chair is built by someone. A song is written by someone. A tool is invented and passed on. But in a bootstrap paradox, the object or idea has no point of origin. It exists only because it was passed from one time to another and looped back. The name bootstrap comes from the old saying about pulling yourself up by your own bootstraps, doing something impossible by using yourself as the source. In this paradox, the object seems to exist because it creates itself. The cause and effect feed into each other in a closed loop. Another well-known version involves a time traveler who visits the past and meets a young composer. The traveler gives the composer a sheet of music and says it's a lost work by a famous artist. The composer studies it, changes a few things, and publishes it under his own name. Years pass. The music becomes well known. Later, the traveler hears it, writes it down, and takes it back in time. Again, the question is, who wrote the music? The composer got it from the traveler. The traveler got it from the composer. There's no beginning. This can also happen with inventions. Imagine a scientist receives blueprints for a machine from a future traveler. She builds it, and over time, the design becomes common knowledge. Decades later, the same blueprints end up in the hands of the traveler, who takes them back to the past. The device works, people use it, but no one ever invented it. The idea exists in a loop. The bootstrap paradox challenges our normal understanding of time. We expect events to follow a clear order. First something happens, then something else happens as a result. But in this case, the order folds in on itself. The result becomes the cause. There's no first step, no origin to point to. In physics, this loop is not always ruled out. In general relativity, certain space-time shapes allow for closed time-like curves, paths through space and time that return to their starting point. If you could follow such a path, you might arrive at a time before you left. These loops don't break the math. They follow the rules of the theory, but they create questions the theory doesn't answer. The bootstrap paradox is different from the grandfather paradox. In the grandfather paradox, you try to change the past in a way that blocks your own existence. That leads to a contradiction. In the bootstrap paradox, there's no contradiction. Everything still happens, but the loop has no beginning. It's logically consistent, but still puzzling. Some theories try to explain this using the self-consistency principle. It says that if time travel happens, it must obey the rules of logic. So anything you do in the past must already be part of history. If you give Shakespeare a copy of his own plays, that must have always been part of the timeline. The plays still exist. They still get written. You just play a role in the loop. But that doesn't explain where the idea came from in the first place. Other theories avoid the paradox by allowing timelines to split. If you go back in time and give someone a book, you don't change your own timeline. You create a new one. In that timeline, the book exists without an author. But in your original timeline, the book had a writer. The problem moves to a new version of reality. The loop is broken because it doesn't circle back to the same universe. This avoids the paradox, but it raises new questions. How many timelines are there? And can you ever return to your own? Quantum mechanics adds more confusion. In some interpretations, information can't be created or destroyed. If the bootstrap paradox involves information with no source, then it breaks this rule. It creates something from nothing. That seems to go against basic laws. But again, the math might allow it if the loop is consistent. Let's take a smaller case. Imagine a pocket watch. A man finds it on his doorstep. He keeps it for years, then meets a traveler from the future. The traveler says he needs a watch, so the man gives it to him. The traveler takes it back in time and leaves it on the same doorstep. The loop is closed. The watch always existed, but who made it? Where did it come from? It was never built. It just moved through time. These loops are called ontological paradoxes. Ontological means dealing with the nature of existence. In these cases, the thing in question exists only because of the time loop. There's no outside source, no original event. It exists because it was brought into the past, and that act leads to its existence again. Some scientists think these loops might be possible under special conditions. Others think they are signs that time travel into the past is not allowed. Still others believe the loops are possible, but the objects inside them can't contain new information. You can't bring a new idea into the past, only something that was already there. That might limit the paradox, but it doesn't remove it. In fiction, the Bootstrap Paradox shows up often. It adds mystery. A person holds a book or tool and asks, "Where did this come from?" The answer is always the same: from the loop, from itself. It creates drama because it goes against how we expect the world to work. The paradox also invites deep thinking. Can something exist without being made? Is time a fixed structure where all events are laid out? If so, loops might be natural, not strange. If time is flexible, then perhaps loops create problems. Either way, the Bootstrap Paradox forces us to think about what it means to begin, to cause, and to exist. The Predestination Paradox happens when someone travels back in time to stop or change an event, but their actions actually cause that very event to happen. The person believes they have free will. They believe they can change the future, but every choice they make ends up leading straight to the outcome they hope to avoid. This creates a loop where the cause and effect feed into each other, and the future becomes fixed by the attempt to change it. This type of paradox is also called a causal loop. It's similar to the Bootstrap Paradox, but with a key difference. In the Bootstrap Paradox, the origin of information or an object is unclear. It exists because it was passed in a loop with no beginning. In a Predestination Paradox, the loop involves events and choices. You go back in time with the goal of preventing something, but what you do ends up causing it. There is still a cause, and it is clear. The twist is that the effect leads to the cause. The loop is tight, logical, and self-contained, but it traps you in a fate you can't change. Imagine a person receives a warning from the future. The message says, "Don't go to the city tomorrow. Something terrible will happen." The person panics and decides to go back in time to stop whoever caused the warning. But in the process of trying to prevent the event, they become the very person who sent the message. The warning exists only because of their own actions. The future they fear happens because they tried to stop it. This is a classic predestination paradox. Another example could involve a fire. A man sees a building burn down and learns that a mysterious figure from the past caused it. He builds a time machine to stop that figure. He travels back, and during a chase or fight, he accidentally knocks over a lamp and starts the fire. He is the cause of the fire he set out to stop. He was always part of that history. His attempt to change it was the very reason it happened. This paradox raises questions about choice and free will. If your future is already written, can you choose anything at all? In the predestination paradox, it seems that everything you do was always part of the timeline. Even your decision to go back in time was already known. You don't change the past, you fulfill it. Your actions were necessary. They happened because the future needed them to happen. In this way, the paradox shows a timeline that is fixed and self-consistent. There are no contradictions. Nothing breaks the logic. you go back to stop something, and you end up making it happen. The events fit together. They depend on each other. The problem is that you can never escape the loop. In some stories, this plays out with tragic weight. Parent goes back in time to save a child, but ends up causing the accident. A leader tries to stop a war, but makes a decision that triggers it. The traveler carries the future on their back, but everything they do becomes part of that future. They were never outside the loop. They were always in it. In physics, the predestination paradox fits with the self-consistency principle. This idea says that any trip into the past must follow the rules of the timeline. You can go back, but you can't change anything in a way that causes a contradiction. Your presence in the past must already be part of history. So if you went back to stop a crime and the crime still happened, then something you did helped make it happen. You were always part of the story. This does not mean you had no choice. You still made decisions. You still acted with intention, but the outcome was already known. Your choices were part of a path that led back to the beginning. They were free choices, but they fit a pattern you didn't see until it was too late. In some theories, this idea makes sense. General relativity allows for closed time-like curves, paths through space and time that return to their starting point. In these models, a timeline can loop back on itself without breaking. But any loop must be consistent. You can't create a contradiction. That means you can't stop the future you already came from. If you try, your actions will simply be part of how that future was made. Let's take a simple version. A woman reads in a history book that a bridge collapsed in the year 1900. She travels back to stop it. She checks the supports and tries to warn people. But in her rush, she drops a wrench. The tool lands in a gear and breaks the mechanism. The bridge collapses. Her effort caused the disaster she wanted to stop. Later, the same history book includes her name as the person involved. She was always there. She just didn't know it until it was too late. These loops feel unfair. They seem to trap people in roles they can't avoid. But they don't break logic. They are strange, but they work. They are part of a consistent universe, one where every event has a cause, even if that cause is itself. Some people ask, could you break the loop? Could you choose not to go back or act differently? In the predestination paradox, the answer seems to be no. The moment you try to change the future, you create the past that led to it. Your actions cannot undo the loop. They form it. The timeline holds together. It resists change, not because of force, but because of structure. In science fiction, the predestination paradox shows up in many forms. A soldier kills a rebel only to learn he was his own father. A scientist tries to stop a virus, but brings it with him to the past. A woman searches for a lost child and becomes her own grandmother. These stories twist time into tight loops. They make the reader ask where the loop started. But that question has no answer. The loop has no beginning. It is closed. The paradox does not mean time travel is impossible. It just means that if time travel happens, the timeline must be self-consistent. Whatever you do in the past must match the future you came from. If the future changes, then you never had that future to begin with. And if you did, then you helped make it. This type of paradox doesn't break the rules of physics, but it changes how we think about time. It suggests that the past and future are not so different. They shape each other. You can act in the past, but your actions might already be written in the future. The loop holds you. You are part of it. You try to stop the future, but you only bring it closer. The story unfolds, not despite you, but because of you. A Novikov self-consistency principle is a rule that applies to time travel. It says that if you travel back in time, everything you do must fit within the timeline you came from. You can't change the past in a way that creates a paradox. If something happened, then it happened that way because of all the events, including your visit to the past. There is no room for contradiction. Time, in this model, protects itself. This idea was proposed by physicist Igor Novikov in the 1980s. He used it to solve the problems that come up when people imagine changing the past. Time travel often leads to what are called causality paradoxes. One of the most famous is the grandfather paradox. In it, a person goes back in time and prevents their own grandfather from having children. If the grandfather never had children, the time traveler was never born. And if the traveler was never born, then who went back in time? The self-consistency principle avoids this kind of loop. It says the timeline is fixed. You can go back in time, but you cannot do anything that would make your own trip impossible. If you meet your grandfather, you can't stop him from having children, because he already did. Your presence in the past must already be part of history. Even if you try to stop something, your actions will become the reason it happened in the first place. This sounds strict, but it does not mean you have no choices. It means that the choices you make will always be the ones that fit the history you came from. You cannot break the loop. You are part of it. Let's take an example. Suppose a man reads that a fire destroyed a library in 1901. He builds a time machine and decides to stop it. He travels back to that year, finds the library, and tries to put out the fire. In the process, he knocks over a lantern. The fire starts. He cannot stop it because he is part of how it happened. He didn't change history, he fulfilled it. His attempt to stop the fire was always part of the story. That's what self-consistency means. Another version could involve a message. A woman receives a strange note that warns her of danger. It's unsigned. Years later, she builds a time machine and sends the warning to her past self. She becomes the author of the message. But the message existed the whole time. There's no paradox. It came from the future, returned to the past, and looped back. This is a closed loop, but it's consistent. The Novikov Principle says that all closed time-like curves, paths through space and time that return to their starting point, must be self-consistent. These curves are allowed by general relativity. They are part of the math, but they raise hard questions. How can a timeline loop back on itself without breaking? Novikov's answer is, it can loop, as long as it stays consistent. This idea has been explored in thought experiments and simulations. One study used quantum circuits to model how particles might behave in a time loop. The results showed that the system found a way to avoid contradiction. Every outcome followed a path that preserved consistency. Even when the model allowed for strange behavior, it always avoided logical breaks. The Novikov Principle is not just about rules, it's about structure. It treats time like a full map. All points on the map exist. Your trip to the past is one point. Your future is another. Nothing you do can change the map because the map includes your actions. You don't rewrite the story. You follow a path that was always there. This can feel strange. People want to believe they can change the past. But if the past can be changed, then history becomes unstable. One change can ripple forward and erase everything. The Novikov model avoids that. It says history is stable because it includes every effect of time travel. Any trip to the past is already part of the past. Let's say a scientist goes back to meet a famous inventor. He wants to share modern knowledge. He gives the inventor a book on new technologies. The inventor reads it and uses the ideas to build early versions of the same machines decades later. The scientist is born into a world where those machines already exist. He studies them, learns their design, and writes the same book. Then he goes back and gives it to the inventor. The loop is closed. The book has no true origin, but the loop is consistent. It causes no paradox. This kind of loop is called a Bootstrap Paradox. The Novikov Principle accepts it, as long as the events stay logically sound. The book exists because it was passed through time. That's unusual, but it doesn't break anything. What matters is that the timeline makes sense from start to finish, even if the start and finish are the same point. Some critics argue that this view removes free will. If you're part of a time loop and everything you do must match history, then how can you make real choices? But the Novikov model does not say your actions are forced. It says they are limited. You are free to act. But all your actions will fit the history that already includes them. You cannot break the timeline, but you can fulfill it in many ways. Others see this as a strength. It makes time travel less chaotic. If the past could be changed, then every trip back might create a new timeline. That leads to branching worlds and endless versions of history. The Novikov Principle keeps things clean. There's one timeline, and it stays whole. This model also fits with how general relativity treats spacetime. In that theory, space and time are linked. Events do not unfold. They are laid out like points on a graph. Your presence at any point is just one part of your world line. If your world line bends back, then you visit the past. But the line stays fixed. It doesn't shift or rewrite itself. That's what consistency means. You can imagine it like a movie film. All the frames already exist. You can jump from one to another, but you cannot change what each frame shows. Your trip into the past is one of those frames. What you do there is part of the movie. You might surprise yourself. You might even cause events you didn't expect. But nothing will happen that breaks the logic of the film. So if you meet your younger self, you must act in a way that fits your memory. If you give advice, it must be advice you already received. If you try to change the past, your attempt must become the reason the present is the way it is. That's the heart of the Novikov self-consistency principle. Time loops can happen, but they must be loops that work. Parallel universes, also known as the multiverse theory, offer a way to avoid time travel paradoxes. The basic idea is simple. If you travel to the past and change something, you don't rewrite your own timeline. Instead, your actions create a new timeline, a different universe with its own future. Your original world stays the same, untouched. The new one grows from the moment you changed. There is no conflict. Both versions exist. This model comes from both science fiction and some interpretations of quantum physics. It solves problems like the grandfather paradox. In that paradox, you go back in time and stop your grandfather from meeting your grandmother. That would mean your parent was never born and neither were you. But if you were never born, how did you go back to stop the meeting? That's a contradiction. The multiverse theory avoids this. You go back and stop the meeting. That creates a new branch, a timeline where your grandfather and grandmother never met. You will never be born in that world, but you still came from your original world where they did meet. You are not erased. You just switched to a different path. It helps to picture time as a tree. Your original timeline is one branch. When you go back and change something, you grow a new branch. Both exist. You just moved from one to the other. The past in your new branch is different, but the past in your old one is still there. This idea comes from the many worlds interpretation of quantum mechanics. In that view, every possible outcome of a quantum event creates a new universe. If a particle can spin up or down, both outcomes happen in separate worlds. You only see one, but both are real. The universe splits with each choice. Applied to time travel, it means your trip to the past doesn't break the old timeline. It just adds a new one to the collection. Let's say you travel to the year 1950 and give someone a future invention. That person uses it to change history. New technology spreads earlier than it did before. When you return to the future, it's not the one you left. Everything is different. But your original future still exists in another branch. You didn't erase it. You just left it behind. This model means there's no single timeline. There are many, perhaps an infinite number. Each one holds a different version of events. Some may be nearly the same. Others may be wildly different. Every time someone makes a choice, or a chance event goes one way instead of another, a new branch might form. This avoids paradoxes. If you go back and change the past, you can't undo your own reason for going back. You didn't come from the timeline you just changed. You came from another one. There is no contradiction, because you never remove your own starting point. That version of history still exists, just no longer linked to you. It also means you can interact with people in the past without breaking the future. Say you go back and give your past self advice. In your timeline, you didn't get that advice. But now, in the new branch, your past self hears it. That self grows up in a different world. You didn't change your life, you helped create a new one. Your own memories stay the same, because you didn't come from the world you changed. This kind of thinking allows for full freedom of action. You can make big or small changes. You can take risks. You can test what happens. Whatever you do, you will not erase yourself. You will not create a paradox. You'll just create a new universe. There are still open questions. For example, what happens to the traveler after the timeline splits? Can they return to their original branch, or are they stuck in the new one? Some versions of the theory say it's a one-way trip. Once you move to a new branch, you can't get back. Others suggest you can navigate the multiverse, moving from one timeline to another like paths in a forest. But this would need rules, tools, or laws we do not yet understand. Another question is whether the traveler affects the timeline by just being there. If you go back in time and try not to change anything, does your presence alone change events? Do small interactions, like stepping on a bug or speaking to a stranger, grow into large changes? In the multiverse theory, the answer is often yes. Even tiny changes create new branches. You don't have to kill a key figure or invent a new machine. Just being there is enough to shift the flow of events. This can be both freeing and troubling. On one hand, you can act without fear of paradox. On the other, every action has weight. Every step, word, or mistake might start a new world. This raises ethical questions. Are you responsible for what happens in the new timeline? If people suffer because of your actions, do you owe them anything? If you create a better world, can you take credit? These are not science problems. They are moral ones. But the multiverse model brings them into view. Let's take another example. A woman loses her family in a disaster. Years later, she builds a time machine. She travels back and tries to stop the event. She succeeds. But when she returns to the future, she finds strangers. Her original family is gone. She saved another version of them in another branch. Her past is untouched. Her future is now different. She cannot get back what she lost, but she has created a world where it didn't happen. In this theory, nothing is truly erased. Every action lives on in a different universe. That includes the traveler's original world. It's still there, even as she can't return to it. Every new timeline becomes its own story, its own chain of events. There is no central timeline, no master version of history, just an endless number of realities, each shaped by different choices. Scientists have not proven the multiverse exists. It remains a theory, but it fits with what we know from quantum physics. It also gives time travel a clear rule. You can change the past, but not your past. You can't go home and undo your pain. You can only visit a different version of it. In that version, things may go better or worse, but your own path stays the same. This model of time travel removes the fear of breaking reality. It says the universe can handle change. It can grow new branches whenever needed. Each one is real, each one is valid, and each one starts the moment you act. In The Time Machine, H.G. Wells introduced a clear, mechanical way to travel through time. The idea was simple: build a machine that lets a person sit, push a lever, and move forward or backward in time, just like a boat sails across water or a car moves down a road. This image shaped how generations of people imagined time travel. It gave time a direction and a method. You could see it, touch it, and steer it. The machine itself was not magic. It was a tool: metal, glass, and levers. Wells described it in physical terms. It had a saddle-like seat, a large spinning disc, and controls the traveler could operate by hand. The rider stayed still in space, but moved through time. To those outside the machine, he would vanish. To him, the world around would rush by like a film playing at high speed. Wells didn't spend much time explaining how the machine worked. He used vague references to geometry and fourth dimensions. But he did not rely on real science. What mattered was the concept. Time could be treated like space. If you can move through space in 3 directions, up and down, left and right, forward and back, then maybe time is a 4th direction. If you build the right vehicle, you could move along that axis. The time traveler, as Wells called him, tested the machine in small steps at first. He built a model and watched it vanish. Then he climbed into the full-sized version and pushed the lever forward. At first, the lab around him blurred. The clock's hands spun. The sun rose and fell in seconds. Then buildings crumbled, seasons flashed, and years rolled by in minutes. Time was no longer a slow flow. It was a force he could control. This image changed how people thought about time. Before Wells, time travel was rare in stories. Myths might use dreams or magic to move between eras. But Wells gave it a frame. The traveler was a person, not a ghost or a spirit. He used a device, not a spell. Time was not a fog or mystery. It was a track. The machine gave direction. The traveler gave choice. In Wells' story, the traveler first went to the year 802,701. There he found the distant future of humanity, soft, childlike Eloi above ground, and dark, predatory Morlocks below. He saw what humans might become. He returned to his own time shaken. Not by the trip, but by what he learned. Later, he traveled even further, to the end of the earth. The sun was dim. Life was nearly gone. Time stretched out to a slow fade. The machine never failed. It moved through time with the same force and clarity as a train through space. The real threat was not the tool, but the world it revealed. The past was fixed. The future was unknown. The traveler could visit either, but he could not change them. The machine carried him like a ship. But it could not steer history. This version of time travel has become the default in fiction. Someone sits in a seat, grips a control, and picks a moment. The machine hums. Time bends. The scene fades or blurs, and a new one takes its place. In many stories, the traveler sees years pass like wind. Rain falls up. Buildings grow or vanish. Generations flicker. The journey is smooth, continuous, and visible. It feels like movement, not teleportation. Other stories have built on Wells's idea. Some machines use digital displays with buttons or dials. Others look like cars, elevators, or even doorways. But the core remains. Time is something you can move through if you have the right device. The trip is manual, deliberate, and directional. It starts when you push a switch, and it stops when you pull it back. This view treats time like a landscape. You can explore it, not just remember it. You can visit the future before it happens, or the past after it's gone. The machine gives you that power. It doesn't break time. It doesn't twist it. It moves through it in a straight line. The user controls the speed and the target. The machine also raises questions. If time is a place, why doesn't the Earth's movement matter? The planet spins and moves through space. Shouldn't the machine also travel through space to stay in the same place on Earth? Wells ignored this. He kept the machine fixed in space. The traveler moved through time, and the rest followed. In later interpretations, writers tried to fix that. Some machines move in both space and time. Others are tied to the Earth's surface. Still, most stories follow Wells's example. They show time travel as a smooth ride, like a boat drifting down a river of years. This approach also shapes how we think about changing history. If you can move through time, you might be able to change events. But Wells's story didn't focus on that. The time traveler observed, but he did not interfere. He couldn't prevent the future he saw. He could only learn from it. That made his trip a warning, not a fix. The mechanical method gives time travel a weight. It is not a dream or a wish. It is a job. The traveler must build, test, and use a machine. He must sit, steer, and take risks. He does not fall into another time by chance. He chooses to go. The machine gives him agency, but also limits. It does not tell him what he'll find. It only gets him there. Wells's model still works because it feels real. The device has parts. The traveler makes decisions. The journey takes time. You watch the world change. You feel distance. Time becomes a place you can visit, but also a force you must respect. In most versions of this method, there is no branching timeline. There is one path, and you move along it. A machine doesn't create a copy. It follows a thread. You can go forward, see what's coming. You can go back, see what came before. But you are still in the same world. That keeps the story simple. You see cause and effect. You live with the results. The mechanical time machine may never exist, but as an idea, it shaped how we imagine time travel. It gave us a tool, a traveler, and a track. It made time feel like something we could reach out and touch, and it showed that the true journey is not just through time, but through what we find when we get there. Time turners in the Harry Potter series are small magical devices used to travel backward in time. They look like hourglasses on a chain. When turned, they send the person holding them back a set number of hours, 1 turn per hour. They don't create new timelines. Instead, they take you back into your own timeline. This means you can't change the past in a way that breaks the future. Everything you do after going back must already fit into what has already happened. In Harry Potter and the Prisoner of Azkaban, Hermione Granger uses a time turner to attend multiple classes scheduled at the same time. Later, she and Harry use it to go back 3 hours. Their goal is to save Sirius Black and Buckbeak the Hippogriff. When they return to that earlier point, they must stay hidden. They watch events from a distance and take only the actions that were always part of the timeline. For example, Harry remembers seeing a figure cast a powerful spell to save him from Dementors. When he goes back, he realizes that he was the one who cast the spell. The past didn't change. It happened exactly as it always had. He just didn't understand it at the time. This kind of time travel follows strict causal loops. The present depends on the past, and the past already includes the effects of time travel. The characters can't undo what has already happened. They can only make sure it happens in the right way. If they try to change events in a major way, the timeline may resist or collapse. That's why the use of time turners comes with warnings. Wizards are told not to be seen by their past selves or others, and not to interfere with events that already happened. This approach avoids paradoxes by forcing consistency. You can't go back and kill your own grandfather because your grandfather already lived long enough to have your parent and eventually you. If you go back in time and try to stop him, something will always prevent you from doing it. Your wand fails, someone stops you, or you change your mind. Whatever happens, the result must match what's already known. Your trip back in time becomes part of the timeline, not a way to rewrite it. The time turner limits how far back you can go. In the story, a device only works for small jumps, usually just a few hours. This prevents major changes to history. You can't use it to go back centuries or stop ancient wars. You can't keep turning it forever. That makes the device near stable. It's useful, but it doesn't give you full control over time. Let's say a student uses a time turner to take 2 classes at once. She turns it once, goes back 1 hour, and attends her first class again. She must avoid running into her earlier self. She must follow a set routine. Her presence in the earlier hour must not disrupt what already happened. If someone saw 2 versions of her at the same time, they might become confused or suspicious. If one version made a new choice, it could cause a chain reaction. So the student must keep the loop closed. Every action must lead back to the same future she came from. The time turner works because it follows the Novikov self-consistency principle. That idea says that time travel is possible only if it does not create contradictions. If you go back in time, your actions must already be part of history. You can't change the timeline. You can only make it complete. In the Harry Potter example, All the events that happen after the time jump already include the effects of the time travel. The spell that saved Harry had already been cast. The axe that killed Buckbeak had already missed. When Harry and Hermione go back, they don't change those facts. They reveal how they happened. This kind of time travel can be frustrating because it removes the ability to undo mistakes. If a bad event happened, it will still happen. You can't stop it unless it never really happened in the first place. If you try to change something and you succeed, then the change must have already been part of history. You didn't alter the past, you caused it to unfold as it always did. Still, the Time Turner gives some room for meaningful action. You can take part in events you didn't understand before. You can see things from a new angle. You can help make the outcome possible. In the story, Harry believes someone else saved him. When he learns it was actually himself, he gains a new understanding. He didn't rewrite the past, he filled in a missing part. This model also prevents branching timelines. There is only one timeline. It stays whole. If you go back and do something, that event must already have been there. That makes the world more stable. It avoids the risk of creating new universes with different outcomes. It keeps the story clean and focused. There is one reality, one history, and one future. In fiction, this kind of time travel often leads to tension. The characters must move carefully. They must remember where they were and what they did. They must act in ways that match what was already seen. They can't be too early or too late. They can't make new choices unless those choices were already made. Let's imagine a new example. A wizard sees a fire start in the castle library. He doesn't know how it began. Hours later, he uses a time turner to go back and investigate. He hides behind a shelf and sees his earlier self drop a lit candle. He tries to stop it. But in doing so, he bumps the candle and causes the fire. He didn't change history. He caused the event he thought he was trying to prevent. That's the core of the time turner. You can act, but only within limits. You are not free to undo or rebuild. You are free to take part. The magic works because it respects the timeline. It treats time like a loop, not a line you can erase and redraw. You don't go back to change the story. You go back to finish it. This kind of time travel puts a strong focus on responsibility. If you go back, you must be careful. You must think ahead. You must act with knowledge that you are part of the story now, not separate from it. What you do matters, but only if it fits. In the world of Harry Potter, the Ministry of Magic controls the use of time turners. They know the risk. They fear the damage. Too many changes could destroy the balance of events. So they issue rules. They grant permission rarely, and when one is used, it comes with strict guidelines. That caution reflects a deep truth in this kind of time travel. Time is not fragile, but it is precise. It allows loops, not freedom. It allows understanding, not control. The time turner works because it fits inside the world it comes from, a world of fixed outcomes and hidden parts. When you turn it, you don't escape time. You become part of it. In Back to the Future, time travel takes the form of a modified car, a DeLorean. Built by the eccentric scientist Doc Brown, the car becomes a time machine when equipped with a fictional device called the flux capacitor. The machine runs on plutonium, which powers the capacitor and lets the car break the time barrier once it reaches 88 miles per hour. When that speed is hit, and the flux capacitor is charged, the car flashes with light, vanishes from one moment, and reappears in another. This version of time travel combines science fiction with everyday detail. Instead of stepping into a mystical portal or an abstract machine, the traveler sits in a car. He drives, he sets a date, and when the system activates, he moves through time just like he might drive across a state line. That simple setup makes the idea easy to follow. It feels familiar and exciting. Time travel is no longer locked in theory. It's a matter of horsepower and speed. The DeLorean doesn't work on its own. The car must be outfitted with a nuclear reactor to produce the 1.21 gigawatts needed to power the flux capacitor. This need for plutonium adds urgency to the story. In the first film, Doc Brown acquires the fuel through risky means, which creates complications. When the car runs out of power, time travel becomes impossible. Later, the problem is solved with a device called Mr. Fusion, which allows the machine to run on garbage. But in the beginning, time travel is not easy. It takes energy, timing, and danger. Once the machine is active, the user can choose a target date by entering it on a digital keypad inside the car. The system shows 3 readouts: the destination time, the present time, and the last time departed. These clear displays allow the characters and the viewer to keep track of the jumps. It also gives a sense of control. Time is not a vague setting, it is a number. You can type in October 21st, 2015, and go straight there. The DeLorean's method of time travel does not rely on a self-consistent timeline. It allows changes to the past and future. In this model, the timeline is flexible. If you go back in time and change something, the present will reflect those changes. That makes the story more dynamic. Every action matters. There are no fixed loops. If you stop your parents from meeting, you risk erasing your own existence. This leads to problems. In the first film, Marty McFly travels from 1985 to 1955 and accidentally interrupts the first meeting between his mother and father. His actions threaten his own birth. He spends the rest of the film trying to fix the damage and make sure his parents fall in love. The story shows how small changes ripple through time. If one thing goes differently, the entire future can shift. The DeLorean allows both forward and backward travel. In later parts of the series, the car takes characters to the future and the far past. This opens the story to a range of time periods. Each trip has rules. You arrive at the same location in space, but a different time. So if you travel from the parking lot of the mall in 1985 to the same lot in 1955, the buildings and roads might be different or missing. This raises an important point. The car moves through time, but it does not leave Earth. The user must consider the world around the location. Travel too far in time, and you might land in a place that no longer exists or into a solid object. The DeLorean avoids this issue in the films, but it hangs in the background. Time and space are linked. A safe landing in one period does not guarantee a safe arrival in another. The DeLorean's version of time travel also includes the idea of branching timelines. When characters change events in the past, they create alternate versions of the future. In Back to the Future Part 2, Biff Tannen steals the time machine, travels back to 1955, and gives his younger self a sports almanac. This small act makes his younger self rich and powerful, leading to a dark version of 1985. Marty and Doc return to find a world they no longer recognize. They realize that they have not just changed a few details, they have entered a new version of history. To fix it, they must return to the past again and stop the event that created the branch. This use of branching timelines lets the story explore different outcomes without locking into a fixed past. It also gives weight to the idea of personal choice. Every action you take might not only affect your life, it might reshape time itself. Despite the power of the machine, time travel in the Back to the Future series comes with limits. You must hit 88 miles per hour. You must have enough power. You must avoid meeting yourself or causing events that unravel your own history. Mistakes are easy to make. Fixing them is much harder. The story also explores how memory and identity work across time. When Marty returns to 1985 after his first trip, he finds that his actions have changed his family's life. His father is more confident. His home is nicer. He remembers the old version, but no one else does. This shows how time travel can create a disconnect. You remember one life, but live in another. The DeLorean gives a visual shape to time travel. It moves. It flashes. It leaves fire trails as it jumps. These effects make time travel feel real. You don't just disappear. You burst into the past or future. The moment becomes a spectacle. It shows that something big has happened. This version of time travel invites questions. What counts as the real timeline? Can you return to your exact version of the past? Are there infinite branches? The films don't answer all of these, but the model remains clear. The DeLorean is a vehicle through time, not a theory. It takes you where you want to go. What you do when you get there, that's up to you. By using a car, the story links time travel to something everyday. The DeLorean becomes more than a car. It becomes a symbol of movement through time. It turns a regular trip into something extraordinary. You don't just go somewhere. You go somewhen. You pick the date. You hit the gas. And if everything works, the world around you changes in a flash. The TARDIS is a time machine and spaceship from the long-running British series Doctor Who. It looks like a blue British police box from the outside, but inside, it is vast, larger than most buildings. It can travel anywhere in time and space. The Doctor, an alien known as a Time Lord, pilots it through the universe. The TARDIS is not just a machine. It is alive. It thinks. It makes choices. Sometimes it takes the Doctor where he asks. Sometimes it takes him where he needs to go. TARDIS stands for time and relative dimension in space. It was built by the Time Lords of the planet Gallifrey. Unlike other time machines, the TARDIS exists partly outside of normal space and time. Its outer shell is a disguise called a chameleon circuit. Normally, this lets the ship blend into its surroundings. But in the show, the circuit breaks, and the TARDIS gets stuck as a 1960s police box. The Doctor never fixes it. Over time, it becomes a symbol. People see the box and know that time travel is possible. Inside, the TARDIS is much more than it seems. The main control room has a central console with buttons, levers, and a glowing column that moves when the ship flies. The walls shine with soft light. Corridors stretch in all directions. The ship has bedrooms, libraries, swimming pools, gardens, and endless other rooms. Some of them appear or vanish as needed. The phrase "bigger on the inside" always surprises people the first time they step in. The ship's size is due to dimensional engineering. Its inside exists in a different space than its outside. The exterior acts like a door to a much larger world. This kind of space folding means the TARDIS can carry almost anything and still remain the same size on the outside. It never has to land in a large space. It just has to open its doors. The TARDIS can travel to any moment in time, from the beginning of the universe to the far future. It can also move in space. One trip might land in ancient Rome. Another might go to a distant planet. It flies through something called the time vortex, which connects all points in space and time. The Doctor sets the destination, pulls a lever, and the ship vanishes with a sound like grinding metal and wind. Then it reappears, often with a bump or a shake. Even though the TARDIS is advanced, it does not always go where it's told. It has a will of its own. It may refuse to land somewhere. It may choose a different destination. It often takes the Doctor to places where something important is about to happen. This is not random. It seems to guide the Doctor based on what the universe needs. The TARDIS has a connection to time itself. It knows when something is wrong. The ship protects its passengers. It creates a breathable atmosphere. It translates languages. It keeps people from aging while inside. It can shield itself from attacks. If damaged, it can repair or even rebuild parts of itself. It has defenses, though they are rarely used. Its most powerful weapon is its ability to escape. When the Doctor is trapped or surrounded, the TARDIS can appear, open its doors, and pull everyone away from danger. The TARDIS can also be unpredictable. Its systems are ancient and often unstable. The Doctor is always fixing or adjusting something. Sometimes the ship lands centuries off target. Sometimes it arrives at the right time, but in the wrong place. These mistakes lead to new adventures. The Doctor does not mind. He trusts the ship. He knows it will get him where he needs to go. In one episode, the TARDIS's mind is placed in a human body. The Doctor speaks to it directly for the first time. It tells him that it didn't always follow his commands because it wanted to help. It took him to people who needed saving. It saw time in a way he could not. It chose him as much as he chose it. This moment shows the deeper bond between pilot and machine. The TARDIS can also break time. In rare cases, its presence creates paradoxes. Its advanced nature means it can cross fixed points in history, events that cannot be changed. The Doctor must be careful. Some actions can tear the fabric of time. Others can collapse timelines. The TARDIS helps to stabilize these effects, but it is not perfect. The wrong move in the wrong place can still cause harm. Despite its power, the TARDIS cannot solve everything. It cannot save people who are meant to die. It cannot go to places locked by time. It cannot undo certain events. It has limits. The Doctor knows this. He uses the TARDIS not to escape problems, but to reach them. He steps out to face danger, not to run from it. The ship also changes with the Doctor. Each time the Doctor regenerates into a new form. The TARDIS may change its control room, update its systems, or shift its layout. It reflects the Doctor's new personality. Still, it remains the same ship, familiar, loyal, and full of surprises. The TARDIS does not follow human rules. It is not a car or a clock. It exists in layers. It sees all of time. It remembers the future and forgets the past. It holds paradoxes and mysteries. Some rooms have not been seen in centuries. Some doors may open into places that do not exist anymore. It is as much a part of the Doctor's story as any person. Traveling in the TARDIS is not just about reaching a place. It is about stepping into possibility. You can open the door and find a battlefield, a distant galaxy, or a quiet street from your childhood. You can walk into the beginning of life or the heat death of the universe. The TARDIS carries people across time, but it also connects them to stories. It gives them a chance to witness, to act, and to change. It is more than a tool. It is a companion. It speaks in silence. It listens. It waits. It has seen more than anyone can imagine, and it keeps going. Not because it has to, but because it was built to travel, and because it was built to help. That is the heart of the TARDIS. It is a ship made for time, but guided by purpose, and at its core, it carries not just the Doctor, but the promise that time can be explored, not just endured. In The Time Traveler's Wife, time travel is not a machine, a spell, or a choice. It is a condition. The main character, Henry, has a genetic disorder called Chrono Displacement. His body leaves the present without warning and appears in the past or future. He cannot control when it happens or where he ends up. He does not choose the time, the place, or how long he will stay. It simply happens, like a seizure or a blackout. When Henry travels through time, only his body moves. His clothes, money, and belongings stay behind. He arrives naked, vulnerable, and confused. Sometimes he lands in familiar places. Other times he wakes up in strange surroundings, with no food, no shelter, and no one to help him. He learns to steal, to run, and to fight, just to survive. He trains his body because he cannot stop the travel. He prepares for it because preparation is the only thing he can control. The condition begins in childhood. Henry starts disappearing for a few minutes, then hours, then days. Doctors cannot explain it. Later, scientists name it Chrono Displacement disorder. It is rare. Only Henry seems to have it. They believe it comes from a fault in his brain's time control center. Something similar to epilepsy, but with a twist in space-time. The body responds to stress or strong emotion by jumping through time. Fear, excitement, or even love can trigger it. Henry often returns to the same places and events. He visits moments from his own life, his childhood, his parents' past, or his future marriage. He meets people he already knows or will meet later. This creates a strange kind of memory. At 28, he meets a 6-year-old girl named Claire. At 6, Claire meets a man she will someday marry. Their lives are tied together in a loop. He visits her as she grows up. She waits for him to return. For Claire, the relationship moves forward. For Henry, it moves in pieces. He sees her at different ages. She sees him at different stages of his life. The time jumps follow rules. Henry never meets a different version of himself from a separate timeline. There is only one timeline. When he travels, he steps into a fixed moment. He was always part of that event. Nothing he does changes history. He cannot prevent his mother's death. He cannot stop future events, even when he tries. The outcome stays the same. The world treats him as part of the plan. His presence in the past does not create a new path. It completes the existing one. Still, the experience is painful. Henry often sees things he cannot change. He watches people suffer. He sees his own future. He knows what will happen to his loved ones. He carries that knowledge without power. In one scene, he meets his future self and learns the date of his own death. He keeps the secret for years. It changes how he lives, but it does not stop what is coming. Time travel in this story is not an adventure. It is a burden. It takes Henry away from the people he loves. He misses birthdays, holidays, and quiet moments. Claire waits without knowing when he will return. Their life becomes full of gaps. She builds routines around uncertainty. He tries to be present, but presence is a luxury he cannot guarantee. Their love becomes a practice of patience, not freedom. There is no machine to fix the problem, no spell to reverse it. Henry and Claire try medical tests, therapy, and even gene research. Nothing works. The condition is built into Henry's body. When Claire becomes pregnant, doctors warn them that the child might inherit it. They try again and again to carry a pregnancy to term. Each time, the fetus travels in utero and is lost. The time travel disorder affects more than one life. It touches everyone close to it. Later, they have a daughter, Alba, who also time travels, but she has more control. Her condition is more stable. She can prepare. She can direct it, at least a little. She is not safe, but she is not helpless. Her experience gives hope, but also shows that time travel remains part of her life, not something she can remove. Chrono displacement is not romantic. It brings risk, grief, and fear, but it also brings moments of beauty. Henry and Claire meet in the wrong order, yet still find each other. Their story is shaped by loss, but defined by love. Each meeting feels urgent. Each goodbye is real. They do not travel through time to escape. They travel through time to stay connected. The disorder also changes how they understand time itself. Most people live in a straight line. They remember the past and imagine the future. Henry lives in loops. He remembers the future and relives the past. He sees how events connect. He knows what people will become. He carries knowledge that he cannot explain. Sometimes that knowledge is a gift. Sometimes it is a curse. Imagine knowing the moment you will die. Imagine seeing a loved one before they are born. Imagine losing hours, days, or months from your life without warning. That is what chrono displacement does. It steals time. It gives it back in the wrong order. It changes nothing outside, but it changes everything inside. The story does not focus on the science of time travel. There is no machine to build, no paradox to solve. The disorder follows its own rhythm. It is not about bending the rules of time. It is about living with them. Henry's life is hard because he knows too much and controls too little. Claire's life is hard because she waits without answers. Together, they build a love that accepts change and works with it. The idea of involuntary time travel changes the usual picture. Most stories show people choosing to travel. Here, it is not a choice. It is a condition. The traveler does not steer the journey. He simply endures it. The jumps are not escapes. They are wounds. They pull him away and leave others behind. Chrono displacement turns time into something fragile. You can't keep it. You can't hold on to moments. They pass quickly, or they come too soon. Henry and Claire hold on to each other instead. They write letters. They leave notes. They make plans in pieces. Time is uncertain, but love gives them something steady. In this story, time travel is not a mystery to solve. It is part of the human experience. The disorder forces the characters to face time as it is, unpredictable, sometimes cruel, sometimes full of wonder. They do not conquer it. They live with it. That is their strength. Retrocausality is the idea that a future event can influence something that happened in the past. This reverses how we normally understand cause and effect. Usually, a cause happens first and leads to an effect. You drop a glass and it breaks. You light a match and it burns. Time seems to flow in one direction. Retrocausality suggests that this direction might not be absolute. In some cases, the effect may come before the cause. This idea is not part of everyday life. You don't see coffee cups unbreaking or letters arriving before they are written. But in quantum physics, strange things happen that don't always fit our usual rules. Retrocausality appears in some interpretations of quantum experiments. It does not break the laws of physics. Instead, it offers a different way of thinking about what those laws allow. One key example comes from the delayed choice experiment. Physicist John Wheeler described it as a way to test whether a photon, a particle of light, behaves like a wave or a particle. In this setup, a photon travels toward a device that can measure its path in different ways. The experimenter can choose to measure it as a particle or as a wave. Here's the twist. The choice of measurement can be made after the photon has already entered the experiment. What seems to happen is that the photon waits for the future measurement to decide how it behaved in the past. If you choose to measure it as a particle, it appears to have taken one path. If you choose to measure it as a wave, it appears to have taken both paths. The future choice changes how we describe the past event. This does not mean the experimenter reaches back and changes time directly, but it does suggest that the past is not fully set until the future completes the picture. Some physicists explain this by saying that the whole experiment, start to finish, must be treated as a single, consistent system. Time does not have a simple flow from past to future. Instead, the outcome at the end determines how we understand what came before. The wave or particle behavior was not fixed until the measurement happened. Another experiment that supports this idea is the quantum eraser. In one version, a photon goes through a double-slit screen and then splits into two linked photons. One photon goes to a detector. The other goes to a different part of the experiment, where the path information can be erased or kept. If the path information is erased, the photons show interference, as if they behaved like waves. If the path is kept, they do not. Here again, the decision to keep or erase the path seems to reach back and change how the photon behaved earlier in the experiment. This leads to a puzzle. If the outcome depends on a choice made later, then the future seems to affect the past. That is what retrocausality describes. It doesn't say you can send a message to the past or stop something from happening. It says that the past and future may be linked in a tighter way than we expect. The whole setup may be bound by a rule of consistency. All the parts must work together, no matter the direction of time. This doesn't mean time travel becomes possible. It doesn't mean you can go back and change history. Retrocausality in quantum physics deals with small-scale events, photons, particles, and probabilities. It's not about humans or machines. It's about how measurements affect systems. One way to make sense of this is to think of time as a block. The block universe model treats all points in time as equally real. The past, present, and future are all laid out like scenes in a movie reel. You move through them, but they already exist. In this view, the outcome of an event can depend on things that happen later, as long as the whole timeline remains consistent. The order of cause and effect is less about time and more about logical structure. Retrocausality also appears in some interpretations of quantum mechanics, such as the transactional interpretation. In this model, a wave goes forward in time from the source, and another wave travels backward in time from the detector. The two waves meet and form a handshake across time. This handshake defines the event. The outcome is not determined until both waves connect. Again, the future plays a role in shaping what happens in the past. This interpretation keeps the math of quantum physics intact, but adds a different way of thinking about what happens behind the scenes. It removes the need for randomness or collapse. Instead, it says the system works with full knowledge of both ends, source and detector, and sets the outcome accordingly. Critics of retrocausality say it leads to confusion. If the future can affect the past, what keeps it from causing contradictions? Could we send a signal back in time? Could we undo past events? The answer is no. Retrocausality does not allow new information to appear in the past. It only allows for correlations that stretch across time. You can't use it to send a message. You can't break logic. Supporters say retrocausality helps explain quantum entanglement. When two particles are entangled, a measurement on one instantly determines the state of the other, no matter the distance. This seems to break the rule that nothing moves faster than light. But if both particles share information from the future, the result makes sense. The future measurement ties them together. They match not because one changed the other, but because both match the needs of a future event. This doesn't make retrocausality true. It just makes it one way to interpret the facts. The math stays the same either way. The debate is about how to understand the meaning behind the numbers. Does time flow forward only, or is it part of a deeper pattern where causes and effects are not limited by direction? To explore retrocausality, imagine a detective who finds a clue only after deciding to look for it. The clue seems to have been there all along, but the moment of discovery depends on the future choice to seek it. The past contains the clue, but the future gives it meaning. In this way, events depend on context, not just order. That is the kind of shift retrocausality brings. In science fiction, retrocausality often turns into time loops or paradoxes. A message from the future arrives to warn the past. A person prevents an event that made them send the message. These stories raise real questions, but the physics version of retrocausality avoids paradox. It doesn't change the past, it completes it. Retrocausality remains a topic of debate. Some physicists think it offers a better explanation of quantum behavior. Others believe it complicates things without solving problems. What's clear is that time may be stranger than it seems. Cause and effect may not always move in one direction. In some cases, the future may shape the past, as long as everything stays consistent. Eternal recurrence is the idea that time does not move in a straight line, but instead loops. Everything that happens will happen again. Every moment, every choice, every event will return in exactly the same way. There is no end, no final goal, and no escape. You will live this life, with all its details, again and again, forever. This idea goes back to ancient thought. Early versions appeared in Indian and Greek philosophy. The Stoics believed the universe goes through cycles. It begins, grows, ends in fire, and begins again in the same way. Nothing is lost, nothing is new. Every pattern repeats. In the 19th century, Friedrich Nietzsche gave the idea new life. He asked what it would mean if everything in your life, every joy, mistake, word, breath, had to be lived again and again. Would you curse this fate, or would you embrace it? Nietzsche used the idea not to describe physics, but to test values. He wanted people to imagine time as a wheel, not a line. He believed that accepting eternal return would show strength. It would mean loving your life enough to live it endlessly. To understand eternal recurrence, Imagine rewinding a film and pressing play over and over. Each time, the scenes unfold the same way. You speak the same words. You meet the same people. You feel the same fears. You don't remember past loops, but you live them again and again, exactly as before. This is not like reincarnation. In reincarnation, you return as someone else. In eternal recurrence, you return as yourself, the same self, the same events. Even the smallest ones repeat. The cough you had at age 6, the pebble you kicked at age 14, the last thing you said to someone before they left. Each detail returns. The idea raises questions about time, freedom, and meaning. If your life must repeat, does that remove your choices, or does it give them more weight? If you cannot change the outcome, does that mean nothing matters? Or does it mean everything matters even more? Think of a person standing on a train platform. They hesitate. The train arrives. They step on. In a straight line view of time, this is one moment among many. It happens once and is gone. In eternal recurrence, that moment returns forever. Every pause, every breath, every turn of the head plays out again. It is not one of many. It is part of the whole that repeats. Some versions of the idea suggest that the universe itself repeats. At the largest scale, all matter returns to the same form. The same galaxies form, spin, and die. The same atoms move in the same patterns. Given infinite time and finite possibilities, every arrangement must return. This is a form of determinism. Nothing truly begins or ends. It only cycles. In physics, there is debate over whether this could happen. The second law of thermodynamics says that entropy, or disorder, increases over time. That would seem to block repetition. But some models of the universe allow for cycles. The universe may expand, collapse, and expand again. In each new cycle, the same events might unfold if the laws and starting conditions match. So far, we don't know if this is possible. The idea remains a philosophical one more than a physical theory. Still, the concept touches on modern science. The idea that the universe might restart from a new Big Bang, appears in cyclic cosmology. If matter and energy return to the same states, then patterns may repeat. But physics does not yet say if these patterns would be identical, or if each cycle would be different. Eternal recurrence focuses less on physical proof and more on human experience. It asks you to look at your life and ask, would you live this again? If you knew it would return, would you act the same way? Would you choose differently? Would you celebrate each moment more, or fear it? Let's take a simple example. You're sitting at a table with a cup of tea. You lift it, you drink, you look out the window, birds fly past. In eternal recurrence, this moment returns an infinite number of times. You will always lift the cup. You will always see those birds. This is not just memory, it is reality. Time bends back on itself. You return. Some people find the idea frightening. If nothing changes, what is the point? If mistakes cannot be erased, how can you live with them? Others find it freeing. It removes the pressure to chase something new. It tells you that this moment, right now, is complete. There is no better version coming. There is no final scene to fix it all. You are already in the only story that exists. The idea also challenges guilt and regret. If you cannot change what has happened, and if it will happen again, then you must learn to accept it. You must face it. You must find peace with your own history, even the painful parts, especially those. Imagine someone you hurt. You said something cruel. You cannot take it back. In eternal recurrence, that moment repeats. You say those words again. They feel the same pain. You do not change the moment. You live it. You witness it. Over and over. This does not remove responsibility. It deepens it. Some people use the idea to guide choices. If you knew a moment would repeat forever, would you live it differently? Would you choose more carefully? Would you act with more purpose? The idea becomes a mirror. It shows you how you live when you believe time is short, and it shows how you might live if time is endless. Let's say you meet someone. You laugh. You talk for hours. You part ways, thinking you'll never meet again. In eternal recurrence, you will. Always. That laugh returns. That goodbye returns. You cannot stop it. You cannot extend it, but you can live it fully. This kind of time travel has no machines, no portals, no future tech. It is quiet. It hides in the shape of things. It speaks through rhythm, through echo. It asks you not to escape time, but to feel it more deeply, to recognize its shape. Time, in this view, is not a road, but a ring. Not a flight, but a breath. Always returning, always familiar, always here. Simulated time travel does not move your body through time. It moves your mind. It uses advanced virtual reality, memory recordings, or neural interfaces to recreate the past. You don't vanish or teleport. You stay in the present, but you experience another time so clearly, it feels real. You might see a city as it looked a century ago. You might hear voices long gone. You might walk through moments that shaped your life or your family's life. All of this happens to simulation. This kind of time travel starts with data. To recreate the past, you need records. Photographs, video, sound recordings, written documents, and scanned objects form the base. More advanced systems might use motion capture, 3D scanning, and AI to fill in the blanks. In a rich simulation, you don't just watch history, you step into it. You turn your head and see buildings rise around you. You speak and people answer. You reach out and objects respond. It's not memory, it's reconstruction. Imagine a historian using this tool. She wants to study life in a Roman marketplace. She enters a chamber, wears a headset, and connects to a program built from ruins, texts, and artifacts. The simulation places her in the mill of the market. She hears Latin spoken, smells baked bread, watches coins change hands. Every sound and detail reflects what researchers believe was true. She doesn't change anything. She only observes. She moves through time, not by leaving it, but by recreating it. The same idea works for personal history. Someone might revisit their childhood home. If records exist, photos, video, perhaps old sensor data, they can step inside that space again. They can look at the walls, hear the voices, feel the light. The brain accepts the illusion. For that moment, they are back. This doesn't rewrite the past. It doesn't allow time to be changed, but it offers presence. The memory becomes a place, not just a thought. Some systems use brain data. If someone wore neural sensors during an event, the signals from their brain could be saved and later played back. This isn't just video, it's perception. The person felt something, and the pattern of those feelings was stored. Another person might access the pattern and experience it secondhand. They don't become the original person, but they feel a version of what that person felt. The past is not only seen, it is shared. This raises ethical and emotional questions. What does it mean to live someone else's memory? Is it real? Is it respectful? If a person's memory is painful, should it be shared? Or if it's joyful, should it remain private? These are not questions of time travel physics. They are questions of dignity, consent, and meaning. In simulation, the past is not locked. It is replayed. Think of a museum that offers visitors a walk through the Great Depression, not with photos on walls, but with a street they can enter. They see soup kitchens, hear speeches, and feel the cold. They don't just learn facts, they live the context. This changes how history is taught. It moves from reading to being. Some companies explore simulated travel as therapy. People with trauma might revisit events in a safe, controlled way. They view the moment again, this time with help. Or they might explore a calm version of a painful memory. The past stays the same, but the person's experience of it shifts. This can help healing. It allows people to face the past with new tools. Other systems explore fictional times. A person might step into a novel set in the 1800s. They don't go to the real past. They go to a created one, but it feels real. It teaches the same way. It builds empathy and understanding. The boundaries between history and imagination blur. What matters is the clarity of the experience. Simulation also allows trial and error. Urban planners might walk through a model of a future city built on old streets. They test how the past fits with the future. They see how people moved, how space was used, and what changed. They make better choices because they see the full picture. In some systems, users can change details. They walk through the past and ask, what if? What if this person turned left instead of right? What if the letter arrived a day earlier? This does not change real history, but it lets people think about cause and effect. They see how one moment shaped another. This helps in education, law, and public memory. Simulated time travel does not rely on wormholes, flux capacitors, or paradoxes. It relies on presence. The user feels they are there. The mind fills in gaps. The brain accepts what it sees and hears. For the person inside the simulation, time bends. The clock says now, but the senses say then. This kind of time travel is safe. There is no risk of changing history, no danger of meeting your past self, no question of paradox. You are not really in the past, you are in a model of it. But the emotional weight is real. Seeing someone who has died, hearing a voice long lost, these things carry meaning. They give people a way to revisit grief, love, and identity. The more advanced the simulation, the deeper the effect. If smell, taste, and texture are added, the line between memory and experience gets thinner. Some people may leave the simulation changed. They may carry the memory as if it were real. They may grow from it. This kind of time travel asks different questions than science fiction. Not can we change the past, but can we learn from it more clearly? Not what if we undo this, but what if we understood it better? A goal is not escape. It is contact. Imagine a person visiting a digital archive of their grandmother's life. She lived in a small town in the 1930s. Her diary, old photos, and audio tapes create a framework. The system builds the streets, the shops, the school. The person walks those roads. They see her house. They hear the sounds she heard. They follow her path. It does not bring her back, but it brings back the world she lived in. This is not magic. It is design. It does not promise power. It offers understanding. In a world where the past fades fast, simulated time travel gives us a way to remember not just with facts, but with presence. It helps us see who we were, so we better understand who we are. A time loop is a situation where a person becomes stuck, reliving the same stretch of time again and again. The day or event resets each time, often after the person dies, falls asleep, or reaches a specific point. Other people don't notice the loop. They repeat the same actions each time, unaware that anything strange is happening. Only the person trapped in the loop remembers what came before. This setup creates a world where actions have no lasting consequence beyond what the main character learns and remembers. If they make a mistake, they get another chance. If they die, they wake up at the start again. This can feel like a curse or a gift. It depends on how the person handles the loop and what they do with their knowledge. In the movie Groundhog Day, the main character, Phil, wakes up every morning to the same song on the radio. The date is always February 2nd. No matter what he does, he ends up back in the same bed at the same time. At first, he reacts with confusion, then frustration, then indulgence. He eats whatever he wants. He breaks rules. He steals. But none of it matters. The next morning always resets everything. Nothing sticks. Later, Phil tries to improve himself. He learns piano, he studies French, he helps people in town. The loop gives him time, more time than anyone usually gets, to become someone better. He can learn from every mistake, he can practice every skill. He becomes the best version of himself, and when he finally escapes the loop, it happens because he has changed. In Edge of Tomorrow, the time loop has a military setting. The main character, a soldier, gains the ability to restart the day each time he dies in battle. The enemy is a species that uses time manipulation, and he gets caught in their system. Each death brings him back to the day before a major invasion. He trains, he fights, he learns more each time. Eventually, he becomes a skilled fighter and begins to find a way to stop the war. His progress depends on memory and effort. He dies again and again, but each loop gives him new information. In both stories, the loop is a trap and a tool. It forces the character to face the same problems until they find a solution. The world doesn't change, so they must change. Their choices shape the outcome. They are the only variable. Time loops raise questions about choice and meaning. If everything resets, does anything matter? If people forget what you did, why try? In most stories, the answer is personal growth. The loop ends not because the character breaks the rules of time, but because they learn something vital. They grow past selfishness or fear. They see others more clearly. They act with care. Not for reward, but because it is right. From a technical view, time loops don't need a clear cause. Some stories explain them with science, an alien power, a quantum effect, or a machine. Others leave it a mystery. The loop just happens. The focus stays on the person inside it, not the rules around it. A time loop doesn't have to be one day. It could be an hour, a week, or a single moment. What matters is that time resets to a fixed point, and the person must start over from there. Imagine someone stuck reliving the same 5-minute conversation with a loved one who is about to leave forever. Each time, they try to say something different, hoping it will change what follows. The loop traps them, but also gives them endless chances to get it right. Loops can be played for humor or horror. In a comedy, the loop may show someone making silly or selfish choices, learning slowly over time. In horror, the loop may trap someone in a violent or hopeless cycle. The tone changes, but the core idea remains. Time repeats, and only one person remembers. This idea works well in storytelling because it focuses attention. The setting stays the same. The people stay the same. What changes is the one person with memory. The audience sees how that memory shapes action. They watch mistakes turn into progress. They see how the same moment can carry different meaning when viewed in a new way. Imagine a student stuck in the same exam. Every time they fail, the day resets. At first, they panic. Then they start to study. Over many loops, they master the subject. They also begin to notice other people in the room. Their stress, their effort, their silence. The student becomes not only smarter, but more aware. They use the loop to grow in both skill and empathy. In some stories, more than one person is aware of the loop. This can change the dynamic. Now, the characters work together. They share plans. They test outcomes. This makes the loop more like a puzzle. They try to find the right series of steps that will break the cycle. It becomes a team effort. Time loops can also highlight how people use time. With no limits, how do you spend your day? Do you waste it, perfect it, help others, give up? The loop makes each action feel both empty and full. Nothing sticks, but everything teaches. You cannot carry anything forward. No money, no fame, no record. Only memory moves through the loop. That memory becomes your only tool. Imagine a parent reliving the last day with their child. Each loop, they try to change the outcome. They try to save the child, but the end stays the same. Over time, they stop trying to change it. They focus on presence. They listen. They hold their child. They learn that even if they can't stop the loss, they can shape the time they have. The loop becomes a lesson in presence, not control. A time loop traps the body, but frees the mind. It removes risk, but demands growth. It removes progress, but demands effort. It makes you start over, but not forget. Each loop is the same from the outside, but inside, for the person who remembers, everything changes. Time loops do not follow normal physics. They are not real in our world, but they reflect real ideas, how people learn, how change takes time, and how moments gain meaning through repetition. They offer a clear picture of growth. Same day, new self, again and again, until it matters. Chrono-Tourism is the idea of traveling to the past or future for leisure. Instead of visiting another country, you visit another century. You might walk the streets of ancient Athens, attend a coronation in medieval England, or watch a space launch from decades before your birth. It's a form of time travel built around exploration, not escape. You don't change history, you observe it. You take in the sights, sounds, and lives of people in other times the same way you might visit a museum or a foreign city today. This idea assumes major breakthroughs in time travel technology. You would need machines that allow safe, targeted, and reversible travel through time. The traveler must leave no trace, affect nothing, and return without error. The system would need strong limits. It could lock the visitor into a passive role, like a ghost, so they cannot touch, speak, or interfere. In some versions, travelers might exist just outside of regular time, able to watch but not be seen. Think of it as a high-tech observation deck overlooking history. A chrono-tourist might choose their trip from a catalog. Each tour could offer a different period, location, and focus. One trip might let you witness the building of the pyramids. Another could show the birth of jazz in 1920s New Orleans. You pick based on interest, just like with modern travel. Tour operators could tailor trips by era, region, or theme. Some might focus on ordinary life, markets, schools, festivals. Others might center on major events, battles, speeches, discoveries. Imagine a tour company offering a week-long Ancient Rome Essentials package. You spend a few hours each day in different areas of the city: forums, temples, bathhouses. Guides brief you before each visit. You learn what to expect, what to watch for, what cultural norms to keep in mind. You don't interact. You don't leave the viewing zone. You watch, listen, and take mental notes. You're not there to be seen. You're there to see. This approach avoids changing the past. The company would use strict protocols. The machine returns you exactly to your own time. No historical drift, no contact, no contamination. Some models might use a kind of time bubble, sealed from the environment. You move through time inside a secure frame, like a glass capsule. It adapts to the time around it but stays closed. That way you get the sights and sounds, but never risk damage. There could be different levels of experience. Some tours might offer visual and sound access only. Others might simulate touch, smell, or temperature. A fully immersive trip might feel like walking through a living city. You hear the horses, smell the food, feel the dust in the air. Your senses accept it as real, even if your body is still protected inside a field or suit. You observe life as it was, not as a movie, but as a moment. Chrono-tourism could serve education as well as curiosity. Students could take a 1-hour trip to watch the signing of an important treaty. Scientists might watch a volcanic eruption or animal migration from the past. Doctors could study early surgeries, battles, or living conditions. Historians could verify records. Artists could study the real colors, textures, and rhythms of a lost time. It's not just for fun, it's for knowledge. But it would come with rules. There would be no stopping to collect souvenirs, no removing artifacts, no warning people of future events, no telling a blacksmith how to build a radio. The entire trip would need oversight. Trained operators would monitor every move. Trips would be logged. Behavior would be recorded. Any act that threatened to change history, even in small ways, would cancel the trip or bring the traveler home instantly. There would be legal issues. Would you need permission to view certain moments? Could you watch someone's private life if they lived centuries ago? Would certain time periods be off-limits? If a trip took you to a violent event, would that be treated like watching a documentary? Or would it cross a line? These questions would guide policy. Not everything in time would be open for tours. You would also need to prepare travelers. Before each trip, you'd receive detailed training. You'd study the setting, the language, the customs. You'd learn what to expect and what to avoid. You'd agree not to judge, speak, or act. Just observe. A careless look or laugh, even if no one can hear it, could shape your memory in a way that distorts the truth. The goal is respect, not performance. Some experiences might be brief. A 5-minute glimpse of the first Olympic Games. A 3-minute moment inside a crowded ship at sea. These short views would still carry weight. You'd see what people wore, how they moved, what they feared. The human part would come alive. These snapshots could replace textbooks in many ways. You might also visit the future. This is harder to define. We don't have future records to confirm what we see. If chronotourism allows trips forward, the experience would be more speculative. It might rely on timelines that change. You visit one version of 2300, then return to find your world has shifted slightly. These trips might be more restricted. They might be one-way views with no lasting access. Some people would use chronotourism for personal reasons. They might want to see lost relatives, forgotten homes, or vanished cities. Someone might visit a street from their childhood. Long before it was torn down, another might watch their ancestors arriving in a new land. These private tours would need care. Emotional impact would be high. People might find comfort, grief, or clarity. This could also raise questions about memory and reality. If you watch your own birth, are you the same person? If you watch a family tragedy, does it change how you live now? Time travel doesn't just show history, it changes how you feel about it. Seeing the truth might be healing, but it might also be hard. Imagine a person standing in the crowd as Martin Luther King Jr. speaks. The voice echoes. The mood feels electric. The moment isn't just read, it's lived. That moment sticks. The traveler brings it back. They remember it with all their senses. They tell the story not as a quote, but as something they witnessed. That power shapes how they see the world now. Chronotourism would need safeguards, training, limits, and deep care. But it offers a new way to explore time, not by rewriting it, but by walking through it. It gives us a different kind of history, not distant, not secondhand, but seen. It lets people visit the past with open eyes and come home changed, not by what they did, but by what they saw. Quantum consciousness time travel is not about moving your body through time. It's about moving your mind. In this idea, your consciousness, your sense of self, your awareness, leaves your present and enters your body at a different point in your own timeline. You don't see yourself as a separate person. You become that earlier or future version of yourself. You wake up in your own body, but at another point in your life, with full memory of where you came from. This idea appears in fiction. In Project Almanac, teenagers use a time machine to go back and inhabit their own past bodies. They live those moments again, with knowledge from the future. In Assassin's Creed, a descendant accesses ancestral memories through a machine called the Animus. He experiences the past as if he were living it firsthand. The body stays in the present. The mind moves back, steps into another life, and sees history through that person's eyes. Quantum consciousness time travel works on the idea that memory and identity are not locked to the present moment. If you can map the mind, its structure, signals, and energy, you might be able to shift that pattern through time. You don't send molecules, you send information. Your brain becomes the broadcast. Your past self becomes the receiver. One version of this idea uses neural resonance. The brain, at different ages, produces different frequencies, but each version of you is still you. If you can match the frequency of your brain at age 16, for example, and then link your current mind to it, the two can align. Your older self's mind overrides the younger one's. You wake up in that moment, knowing what you know now. This opens up all kinds of questions. If you change something while living in your past body, do you change your future? If you know your future, can you avoid mistakes? In some versions of the theory, the timeline shifts. You return to the present and see a new outcome. In others, the past cannot be changed. You were always the version of yourself who had traveled. Every choice you made already included that knowledge. Let's say you shift back to the day of a job interview that you now regret. In your original past, you were nervous, unprepared, and didn't get the offer. But now, with your older mind in your younger body, you approach it with confidence. You say the right things, you get the job. The rest of your life changes. When you return to your present, you remember both versions. The new reality is the one you wake up in. This method of time travel depends on quantum theory in a loose sense. It treats consciousness as a pattern that might exist outside time. Quantum physics shows that particles can link across time and space. If the mind is a quantum system, it might be able to jump through those links. Not the whole brain, just the information. Your thoughts, your awareness, your identity. Those could be what moves. Some theories suggest that time is not linear, but a landscape. Every moment exists at once. The present is just where your mind happens to focus. If you could shift that focus, you might step into a different moment. The past is not gone. It's just not being looked at. You redirect attention, and the mind locks on to a different point. This also connects to memory. When you remember something, your brain reactivates the pattern of that moment. If that pattern is complete enough and you amplify it, the memory becomes a bridge. You could, in theory, ride that pattern backward and inhabit your body at that time. But only if that body still exists and can support the mind that enters it. There are limits. You can't travel to a time before your own brain existed. You can't enter someone else's life. You are tied to your own timeline, your own biology. You are not moving through space. You are moving through self. That makes this a personal form of time travel. It's not for history books. It's for decisions, regrets, second chances. The risks are deep. If you change something and it doesn't go the way you hoped, you can't always undo it. If you shift into a painful moment and can't leave right away, you may have to live through it again. If your mind breaks the link while in the past, you may become stuck. Or your younger mind might return, forgetting what you tried to change. There's also the issue of memory stacking. If you keep jumping back and living the same period over and over, your brain carries the weight of all those versions. You remember hundreds of trials, but the people around you don't. That creates distance. You become someone they can't understand. You live a life they never saw. Some versions of the theory allow for future jumps. You shift forward and wake up in your older body. You see how your life turned out. You feel the changes in your body. You meet people you haven't met yet. You get to test the future, then return. But the risk is that you might not be able to understand what you see. Or you might become obsessed with avoiding what's coming. You might try to fix something that hasn't happened yet, and in doing so, cause it. Think of a teenager jumping forward and seeing himself at 50. He sees the house, the job, the face in the mirror. Maybe he's happy, maybe he's not. When he returns, he starts to push for that future, or reject it. Either way, he acts with knowledge most people never get. His life becomes shaped by what he saw, not what he wants. This form of time travel doesn't need big machines. It needs deep control of the brain. It needs a way to isolate the mind, store it, and transmit it. Maybe one day people use a chair and a headset. They lie back, close their eyes, and drop into their own past. Or maybe it's done through dreams. Your sleeping brain reconnects to a younger self, and you wake up years earlier. It raises hard questions. If you return and change a painful moment, is the new version of your life more true? What happens to the version you left behind? Does it disappear, or does it keep going in another branch? Can you live with the knowledge of all the lives you didn't choose? Quantum consciousness time travel turns time inward. You don't escape time. You enter yourself. You look back, not from outside, but from within. You carry your mind across years and meet the person you once were, not as a stranger, but as a host. You take the same breath, but with new eyes. You walk the same path, but with different thoughts. You travel through time by remembering, by shifting, by returning to where you began, with the full weight of who you've become. Post-mortem time travel is the idea that after death, a person's consciousness returns to an earlier point in their own life. They wake up as their younger self, but with full memory of the life they already lived. The world continues as if nothing strange has happened, but the person inside is different. They remember everything: who they were, what they did, what they lost, and what they regret. Now they have the chance to live it all again. This concept is not based on machines or external forces. It doesn't require wormholes, quantum computers, or time-traveling devices. It takes place within the self. The body dies, but something survives. That something, call it the mind, the soul, or simply memory, returns to an earlier version of the same life. The new loop begins without warning. The person might die at age 60 and wake up at 18, or they might restart at 45, 25, or even as a child. The point in time varies, but the core idea stays the same. Death becomes a doorway to a repeat. In the novel Replay by Ken Grimwood, this idea forms the heart of the story. The main character dies suddenly in his 40s and wakes up in his college dorm room as his younger self. He carries the full knowledge of his past life. This includes personal experiences, relationships, and even world events. He uses that knowledge to make new choices. At first, he tries to profit. He bets on sports, invests in companies before they grow, and lives without fear. But each time he dies again, he returns, sometimes at a different point, and must start over. Each replay teaches him something. He tries different paths: wealth, love, risk, isolation. Over time, the experience changes him. He starts to ask what matters, not just what's possible. This form of time travel raises deep personal questions. If you could live your life again with everything you now know, what would you do differently? Would you avoid certain people or seek them out sooner? Would you take bigger risks or play it safe? Would you try to stop tragedies or accept them as part of your story? In a normal life, hindsight arrives too late. Post-mortem time travel brings it early, when it still has power. It's different from traditional time travel because the world itself doesn't change. History stays the same. The people around you stay the same. Only you change. You live among others who don't know what's coming. You know what they will say, how they will act, and sometimes even how they will die. That knowledge can create distance. You no longer fit. You carry too much experience. In a room full of students, you feel like a stranger. In a conversation with your parents, you feel the weight of the years that haven't happened yet, but already have. One of the clearest examples of how this works is through decision-making. In a normal life, you might worry for years about a job you didn't take or a person you didn't talk to. In a post-mortem replay, you get that moment again. You know what happened the first time. Now you can choose differently. That choice might bring peace or more regret. You never erase the past, you simply build a new one beside it. In some versions of this idea, the loop is endless. You die, go back, live again, die again, and return once more. Each time you carry more memory, you try new approaches. Some people become wiser, others become more desperate. The experience can bring growth or madness. You might search for the perfect life, only to learn that perfection doesn't exist. Let's take an example. A woman dies at age 70. She had a good life, but carried regret over a falling out with her sister. She never fixed it. After death, she wakes up at 30, just before the fight happened. She remembers everything. She chooses not to say the words that broke the bond. This time, she keeps the relationship. It brings her joy, but also pain. New arguments, new problems, new decisions. The past wasn't perfect, but the new version isn't either. That's the truth of human life, even inside a loop. Another example, a man dies in his 50s, broke and alone. He wakes up at 19, just before he made the choice to drop out of college. He goes back to class, earns his degree, gets a stable job, and builds a different future. But he misses some of the freedom and wildness of the first life. He knows where the road leads, but wonders if he's lost something by avoiding the original mistakes. These loops raise questions about identity. Are you still the same person if you carry decades of extra memory? Do you still feel close to people who don't remember what you remember? What happens when you fall in love with someone who has no idea you've loved them before? Post-mortem time travel doesn't involve changing the world around you with technology. It's a shift inside. The body remains natural. The mind becomes the traveler. This opens possibilities for reflection, for healing, and sometimes for manipulation. If you know what someone wants to hear, you can say it. If you know when someone will leave, you can prepare, but you must still face the same limits. People don't change unless they choose to. You can nudge them, but not control them. This idea also touches grief. You see people who died in your original timeline. You talk to them. You hold them. You know they won't be around forever. That makes their presence more precious. You might spend an entire replay just appreciating the things you once overlooked. Not every version of this concept ends with peace. Some replays become darker. A person may become trapped in loops of guilt, trying to fix something they never truly understood. They may push too hard, knowing what's coming, and end up breaking what they tried to protect. In some stories, the loop ends when a person reaches a kind of understanding. They don't need to fix everything. They don't need to win every time. They need to live with presence, to accept the limits of control. Only then does the loop stop. They die, and this time, they stay gone. Other versions leave the loop open. The traveler becomes a kind of silent guardian of their own past, always reliving, always adjusting. Their life becomes a long test of patience and meaning. Post-mortem time travel shows how much weight memory can carry. It shows that time, for some, might not be a one-way road. It might be a circle or a spiral, always returning, always offering another chance, not to erase the past, but to meet it with new eyes. The time reversal hypothesis suggests that under certain conditions, the entire universe could reverse its direction of time. Not just for one object or one moment, but for everything at once. This doesn't mean clocks suddenly tick backward while people stay the same. It means all processes would move in reverse. A shattered glass would reassemble. Ashes would reform into wood. Thoughts, speech, motion, everything would unfold in reverse, as if the universe had pressed rewind. At the heart of this idea is entropy. In physics, entropy measures disorder. Systems tend to move from low entropy, where things are ordered and structured, to high entropy, where things are spread out and disorganized. A tidy room becomes messy. Ice melts. Stars burn out. This direction, from order to disorder, defines what we call the arrow of time. It's why we remember the past, but not the future. It's why causes come before effects. But the laws of physics, at their core, are time-symmetric. The equations work the same whether time moves forward or backward. If you record two particles bouncing off each other and play the video in reverse, it still looks like a valid outcome. Nothing in the math says time must go one way. So why does it? The answer seems to lie in initial conditions. The universe began in a low entropy state, extremely ordered. Since then, entropy has risen, stars formed, lived and died, galaxies scattered, life emerged, grew complex, and decayed. That rising entropy creates the sense of time flowing forward. But what if entropy stopped rising, or started to fall? According to the time reversal hypothesis, there may come a moment when the universe reaches a maximum state of entropy, complete disorder. If that happens, and if the universe continues to evolve, entropy might start decreasing. If it does, then time, at least as we experience it, might reverse. Not for some parts of the universe, but for all of it. Imagine a universe far in the future. Stars have faded, black holes have evaporated, all matter has broken down into cold, random particles. Nothing more can decay. The universe has no structure left. This is called the heat death scenario, maximum entropy. From this point, if anything changes, it must move toward more order. At that moment, entropy would begin to fall. From our view, time would reverse. In that reversed phase, events would play out in the opposite direction. Particles would clump together. Energy would focus instead of spreading. If life existed in that phase, it would remember the future and forget the past. But to them, that future would feel like our past. Their experience of time would be just as normal as ours, even though it moves in the other direction. It's important to note that this reversal would not feel sudden. From inside the system, it would feel continuous. A being alive during the time reversal wouldn't say, "Time just flipped." Instead, it would experience a smooth timeline, just one that happens to be going in the opposite direction relative to ours. This also means there's no preferred direction of time in physics. Forward and backward are labels we apply based on entropy. If entropy rises, we say time is moving forward. If entropy falls, we say it's moving backward. But in both cases, the physics remains the same. Now think of this on a human scale. Suppose this reversal happened during a time when life still existed. You would live your life in reverse. You would unlearn facts, move from old age to youth, and finally back to infancy. You wouldn't be aware of it though. Your mind would adapt. You'd remember yesterday as what we think of as tomorrow. To you, that timeline would make perfect sense. This idea leads to strange but logical consequences. Imagine a person lighting a candle. In the forward phase, the flame burns down, wax melts, and heat spreads. In the reverse phase, heat gathers from the air, wax reforms, and the candle unburns. The person would see it as lighting the candle, even though the physics plays out backward. Their mind, memories, and choices would all reflect the reversed flow of entropy. One challenge with the time reversal hypothesis is detecting it. If a future phase of reverse time happens and it lies beyond our current era, how could we tell? Could we observe signs that the reversal is coming? Probably not. The transition would be invisible to those inside the system. From our point of view, time would simply stop if entropy reached a ceiling. From the reversed side, it would start again, with no clue that anything had changed. Another question is whether this process could repeat. If time can reverse once, could it do so again? Could the universe expand, reach maximum entropy, reverse, contract, and then repeat the cycle? Some theories suggest a cyclical universe where time alternates direction with each full cycle of expansion and contraction. In that view, time is a loop, not a line. This also affects how we think about the Big Bang. If entropy runs in both directions away from that point, then the Big Bang might sit in the middle of time, not the beginning. One half of the universe moves forward from the bang, and the other half moves backward. Both directions experience rising entropy relative to their own timeline. Both think they are moving forward, Each side sees the other as moving in reverse, but neither is more correct. This kind of symmetry is hard to imagine because we experience time only one way. Our brains store memories in order. Our biology runs in one direction. Our lives follow the flow of rising entropy. But the deeper you go into physics, the less time seems like a fixed path and more like a pattern that depends on your perspective. In short, the time reversal hypothesis says the arrow of time is not built into the laws of nature. It comes from how the universe started and how it evolves. If conditions change, the arrow could point the other way. From inside that system, the shift would feel normal. The past and future would trade roles, and the story would go on. The tape doesn't stop, it just rewinds. Selective time editing is the idea of changing specific parts of a person's past without altering the entire timeline. It's not full time travel. You don't go back in a machine or relive your life. Instead, you reach into a moment, an event, a decision, a memory, and adjust it. You might erase a conversation. You might replace a memory. You might shift one detail while everything else stays the same. The body remains in the present. The change happens at the level of the mind, the record, or the timeline itself. This concept depends on precise control of information. In one version, you use a neural device that edits memory. It doesn't erase everything, just the part you target. You remember the day clearly, but not the part that hurt. Or you forget a name, a face, a feeling. The rest of your memory stays intact. The edit is surgical. The tool reads the brain, finds the pattern, and rewrites it. Think of someone who lost a loved one in a car crash. The trauma sits in one moment: the sound, the sight, the helplessness. With selective editing, they could remove that flash from their mind. They still remember the person. They still grieve. But the sharp edge dulls. They don't relive that second every time they close their eyes. They gain space to heal. Another version focuses on timelines, not memory. It assumes time is not fixed. The past holds many small branches, choices, outcomes, actions. With the right technology, you can reach into a past moment and shift one element. You don't undo everything. You change a single cause. The rest adjusts around it. This isn't just forgetting. It's rewriting the path. Let's say a scientist drops a vial that ruins a key experiment. Years of work are lost. With timeline editing, she goes back and nudges the moment, makes her hand steadier, the table more level, the movement slower. The vial doesn't fall. The experiment continues. Her timeline changes. She doesn't remember the spill anymore. That version of her no longer exists. She remembers a smoother path. The edit rewrites her reality. This raises questions about identity. If your memories change, are you still the same person? If your timeline changes, do others notice? In most versions, the answer depends on scope. Small edits keep most things in place. Big edits ripple outward. If you erase one argument, your relationship stays mostly the same. If you remove years of conflict, the whole structure shifts. The technology behind this would need to track causes and effects. It would scan the timeline, isolate the event, and simulate the change. If the edit causes major damage, someone else vanishes, a key event never happens, it might block the change or warn you. Edits might be limited to protect the larger structure of time. There could be social rules. Maybe you're only allowed to edit your own memories. Maybe certain periods of history are locked. Maybe you get a set number of edits in your life. A registry might track changes to avoid overlap or conflict. A review board might approve or deny requests. Some edits might be emotional. You don't remove the event, just how it felt. A student who failed an exam might still remember the grade, but not the shame. A veteran might recall the mission, but not the panic. This form of editing changes perception, not history. It treats trauma by separating the fact from the feeling. Other edits focus on action. A person might choose to undo a lie, a theft, or a missed opportunity. They replay the moment, choose differently, and let the new version overwrite the old. They return to the present with a new memory, new habits, and perhaps a new reputation. But only if the system allows the change. If someone else's path relies on that moment, the edit might be blocked. Imagine a couple who broke up over a single fight. One partner uses time editing to soften what was said. They reframe the words, choose calmer tones, offer more patience. They return to the present still together. But the bond feels different. One person remembers tension, the other doesn't. That difference might create new distance, even if the edit saved the relationship. Selective editing might also be used for knowledge. A person could remove false beliefs or bad habits. They might erase a pattern of thought that once held them back. Or they could insert useful experience from training programs, muscle memory, focus, calm under pressure. This kind of editing mixes memory with simulation. You learn by living the experience, even if it wasn't yours. But editing carries risk. What happens when memories conflict? If you and someone else both edit the same moment, whose version holds? What if one person deletes a meeting that changed another person's life? Systems would need rules to manage overlap. They might block changes that harm others, or let people compare alternate outcomes before choosing one. Some people might overuse editing. They could chase perfection, polishing every mistake, removing every pain. They might lose the lessons that come from failure. They might forget how to sit with regret or grow through hardship. A life without scars can feel hollow. If nothing sticks, nothing shapes you. Others might fear editing. They might refuse to change anything, no matter how painful. They might cling to memory as truth, even when it hurts. They see the past as sacred. They believe in facing it head-on, not smoothing it over. One story might involve a man who watches his child fall from a swing and break an arm. It's a small accident, but the memory haunts him. He edits the moment, removes the fall. In the new version, they leave the park early. The child is safe, but the bond feels weaker. That moment of comfort in the hospital, the shared recovery, is gone. He learns that not every painful memory should be erased. Another story might show a woman erasing a childhood trauma. The edit lets her sleep. She feels lighter, but she forgets why she moved across the country. She forgets the people who helped her heal. She becomes someone else, shaped by new gaps. The trauma is gone. But so is the growth. Selective time editing could become a tool, careful, limited, personal. It might treat mental wounds, soften regret, correct accidents, but it would need control, restraint, and honesty. Not every error should vanish. Not every pain should be patched. Some things are part of you. The challenge is knowing which ones. This isn't about escaping time. It's about working with it. You don't jump through years. You reach into a moment. You touch it, turn it, and see what follows. You learn what to keep and what to change. Not to perfect your life, but to understand it better, one edit at a time. Digital time cloning imagines a future where a detailed digital version of you travels through time. Not physical time, but through simulated timelines. This clone doesn't exist in flesh and blood. It exists as data, shaped by your memories, choices, habits, and behaviors. Think of it as a thinking, learning copy of you. It can enter simulations of the past or projections of the future and act on your behalf. You stay in the present, but your digital self explores what was or what might be. This form of time travel doesn't involve moving through space-time. It involves building environments so accurate and interactive that your clone can experience them as real. If the past is based on archived data, photos, records, audio, and video, the simulation can reconstruct a moment. If the future is based on trend models, AI predictions and possible outcomes, it can generate what might happen. The clone moves through these landscapes, makes decisions, and reports back. For this to work, you need two things: a strong simulation engine and a high-resolution model of your mind. The simulation must recreate enough detail: buildings, sounds, language, weather, and human behavior for the digital self to respond naturally. The digital self must reflect your personality well enough to act as you would. It doesn't just repeat facts. It responds, adapts, and learns. It doesn't become you, but it comes close. Imagine a system that has studied you for years. It has access to everything you've written, said, bought, or posted. It knows your routine, your mood swings, your values. It builds a behavioral map. From that map, it creates a clone that walks and talks like you, not physically, but mentally. Then the system drops that clone into a moment from your past. Maybe it's your high school graduation, maybe it's a dinner you regret. The clone revisits the scene and interacts with it. You watch from outside. You don't just remember, you see how your other self moves through it. This allows reflection. Instead of guessing how things could have gone, you test it. You let the clone try a different approach. What if you had spoken up? What if you had waited? The system lets you rewind and run it again. You observe the outcomes. Some versions let you experience it through the clone's senses, as if you're there. Others keep you in control, guiding the clone like a director. The same works for possible futures. You feed the system with current conditions: your job, your relationships, your plans. The simulation builds scenarios. What happens if you change careers, move cities, or start a family? The clone plays each version. You don't have to risk real life. You see what unfolds first. This isn't perfect prediction, it's possibility. The clone reacts in ways that match your patterns. It makes informed guesses. Businesses might use digital time clones to model decisions. A company could simulate how you'd respond to a product 5 years from now. They run your clone through future market settings, adjusting price, packaging, tone. They see how you respond, not by asking, but by watching. The digital self provides insight, not opinion. It reflects behavior, not theory. Therapists might use this tool to help people process trauma. They create a safe version of the past, put the digital self into it, and allow it to act. A person can then observe the response, or even enter the simulation to speak directly with the clone. The goal isn't to rewrite history, but to better understand it. The clone can also go beyond your own timeline. If it's trained well enough, it might be placed in any point in history. You could see how your personality would function in the 1800s, in ancient Greece, or in a future Martian colony. The clone learns from the setting and adapts. It shows not just how you behave, but how context shapes you. This raises ethical questions. Who owns the clone? If a company builds it from your data, do you have the right to control or delete it? If the clone continues to learn and evolve, does it become a separate being? Can it make decisions you wouldn't? What if it chooses something harmful in a simulation? Does that reflect on you? There are privacy concerns. If your clone is accurate, it can reveal things you haven't shared. It might express thoughts or feelings that you've never said aloud. If others interact with it, they might learn more about you than you intended. You'd need safeguards, permissions, encryption, usage logs. You'd also face limits of accuracy. No model is perfect. Your digital self is based on past data, not your full inner world. It may miss instinct, intuition, or growth. Over time, it may drift. You might change, but the clone stays the same. Some systems would need regular updates. They'd resync with your life to stay close. Still, the benefits could be deep. You could run through hard choices before making them. You could explore regrets without pain. You could watch younger versions of yourself make different choices, then learn from the outcomes. You could plan ahead with more clarity, not by guessing, but by testing. Imagine a person considering retirement. They create 5 clones, each living a different future. One moves to the countryside, one travels, one starts a business, one stays put, one returns to school. The system runs these 5 lives in fast forward. The person watches the long-term effects: loneliness, joy, stress, health. They see what works. They don't pick the perfect path. They pick the one that feels right after seeing it lived out. Digital time cloning doesn't promise control. It offers insight. You don't change the past. You understand it. You don't predict the future. You explore it. The self that walks through time isn't you, but it carries enough of you to be trusted. It becomes a lens, not to erase or escape, but to examine who you are across time and what kind of life you might still shape.